Hello, everybody. Welcome to Groningen. Welcome to Rocky Worlds 4. Thank you so much for being here. So many people, in fact. It's really exciting for all of us from the organizing team to see you here. I'm Tim Lichtenberg. You got all the emails from me. Sorry about that. And in a few minutes, we will speak a bit about the organization of the conference and sort of like what we can expect the next five days. So we're very excited to welcome you here, the whole University of Groningen, the Kaptein Astronomical Institute. But before we dive into this conference, I would like to give the word to Oliver Schortel from the Rocky Worlds board.
Thanks so much, Tim. Is everyone excited to be here at Rocky Worlds? Yeah! Amazing. Cool. Excellent. So yeah, it's a real pleasure to be with you all here. It's a really special meeting for me and hopefully for all of you as well. Special, but not unusual in the sense that I cannot change my slides. So in that respect, it's like all other meetings. Fantastic. Thank you. So awesome. Cheers, Tim. So I just wanted to give a bit of a kind of potted history of how we came all to be in the room today. So Rocky Worlds began its life in Cambridge in 2020, and Amy Bonza, who'll be here, I think from later today, and I were thinking, what kind of interdisciplinary meeting could we have to connect our two research worlds? So Amy was working on very much dead planets so dead they'd been atomized in the atmosphere of a dead star, white dwarf pollutants. And on the other hand, I've spent most of my career working on the Earth sciences, a planet so much alive it can self-identify as being alive. And we thought, what's the middle ground between these two research areas? Exoplanets, planets that are neither dead nor alive, because in 2020, the rocky portion of that population we knew essentially nothing about, other than the fact they were there. And that was born, the Rocky Worlds, an idea for an interdisciplinary meeting. And 89 brave souls joined us in a cold Cambridge in January for that meeting, right before a global pandemic, of which there's no correlation, I assure you. And it was a fantastic meeting, and we heard everything from giant planets and the lessons that giant planets were teaching us, through to applying our imaginations, creativity, and ideas about what these rocky worlds and their nascent exploration might tell us. What next? Well, if Cambridge does something, there's only one inevitable next step, which is that Oxford must follow 2 years later. So it's Rocky Worlds 2. Now, this is a super special meeting for me, and I think probably for many people, this would have been now the first in-person meeting for almost 2 years since the Cambridge meeting. So it's a huge achievement that meeting happened logistically, that got over now 100 people into Oxford in much better weather than we had in Cambridge to enjoy an in-person meeting about a topic which was just about to be transformed later that year as we transitioned to the JWST era, and actually Rocky Worlds being something we could now begin to think about characterizing. But there was a kind of problem we realized, speaking to Tim after this meeting, which was we'd settled into a Rocky Worlds meeting cycle of every 2 years. But what was obvious is that Rocky Worlds are actually some of the most abundant planets in the galaxy, and once every 2 years, it was going to take us an awfully long time to work through all of them. So how are we going to accelerate the schedule here? And that led to the Rocky Worlds discussion series, launched between the Rocky Worlds 2 and Rocky Worlds 3. This online series, which hopefully many of you are aware of or have participated in, supported by a fantastic group of hosts, many of whom are here, so please chat to them. It's now kind of giving a monthly Rocky Worlds kind of update, the frontier of research across this really exciting area. Then in 2024, Rocky Worlds goes to Zurich, now in the JWST era, with rocky planets actually being something we can think about looking at. And you can see the meetings grown again, now 140 people, a fantastic mark of its success. Bringing us to Rocky Worlds 4 today in Groningen. 180 people, as we can see from the kind of peas in a pod arrangement you've had to adopt with those around you. Really exciting that the meeting's grown so much. And I'd just like to end this kind of potted history just by, if we could say thanks to the LOC at the beginning of the meeting as well, because obviously for us all to be in this room, caffeinated, fed, is a huge achievement already, no matter what happens next. So not that I'm anticipating any problems at all with Tim's peerless leadership, but can we just start by saying thank you to everyone who's put so much in already? Great, so thanks so much for hearing me. I'm looking forward to chatting to you all this week.
Thank you to Ollie. All right, yes, you saw the increasing history of our Rocky Worlds meeting series, and we're excited to have the next chapter happening right now. So what we try to do, we already see now that, you know, the small exoplanets are very diverse in their composition and all their characteristics. And so we try to match that with our conference series, where we try to really be transdisciplinary ultimately, to really encompass all the different fields and disciplines that we need to understand the low mass exoplanets and ultimately also the terrestrial planets and low mass planets in our solar system. And so here's a bit of a recap of essentially the split of our abstracts for the Rocky Worlds conference. So this is mostly divided across what we define sort of the main themes, what we have in mind essentially across atmospheres, which is the most dominant topic, followed here by these three sort of interiors, astrobiology, and then formation. Instrumentation and lab experiments is a bit smaller, and we hope to gain ground actually on this in the following years. But we have some very nice and exciting results also during this conference essentially. And then, because nobody wants to live in those categories, of course, people came up with many different subcategories. So we're very excited to see essentially all the diversity on those themes, and I look forward to speaking with many of you about those. So Rocky Worlds has been and continues to be a very young conference series. So about 50% of our participants and abstracts that we got are from graduate or doctoral researchers. So in my opinion, this really shows that the golden times of the field actually still lie ahead of us, which is really exciting. So we will see what the next years will come to bring so that we can learn about these worlds. And yeah, in terms of we are not only diverse in sort of like topics and career level, but also increasingly diverse in gender expressions. So expressed here by the pronouns. So we have about 60% he, him, about 36% of she, her, and very diverse pronouns that people sort of assign their pronouns like we enable them to give here. And so what we do is we look forward to a really exciting, diverse, and state-of-the-art conference where we learn all together something about these exciting new worlds. Now, oh yeah, and Ollie said this already, we actually have a couple more people coming. It's now about 190, and we actually have close to about 100 online participations. So hello everybody online. It's great that you're here with us. And we have more than 25 countries of origin. So it's a really, really diverse conference, and I think that adds to the strength of the conference series. This is the SOC, the Scientific Organizing Committee. Nearly all of them are in the room. And I really want to thank the Scientific Organizing Committee to help put together an exciting schedule and lineup. We put a lot of thought in how we can essentially objectively and on scientific grounds evaluate all the abstracts and also achieve diversity in themes and in topics and essentially reflect the growth of the field. And so let's thank together the SOC, the work that they have put in once. Please, let's join me. Yeah, and so you can see many of them, so please talk to them. They also do exciting science, and they support many of those activities here over the years and continue to do so. Then, Ollie mentioned this already, the local organizing committee has been putting a lot of work already in the meeting series and in this particular meeting, and you will see many of them throughout the week. You will see them by they're recognizable by their red name tag cards, like this one here. So if you have an issue or a problem or need help or any support, please reach out to one of them, and they can either help you directly or at least they will know who to ask immediately. Who is not here with a picture are Christa Meyering, many of you met her at the registration desk, and Martine Terval, who helped also a lot with the organization of the travel of some of these activities. If you don't want to talk to someone in person, or you have a general question, the LOC is always also reachable here at this email, or if you have joined the Discord channel, you can also put your question directly in the Discord channel by tagging the LOC this way. So we will let's thank the LOC all together already, and then let's do it again. Okay, some quick updates about this. So you see that all our talk sessions are hybrid. That means they are streamed online on Zoom and YouTube. But the talks are only in person, so only people in the room will be able to are presenting. But there can also be questions from online attendees. That means someone from the LOC will read those questions aloud, so we can interact like this with online participants. Poster sessions and the breakout discussions, and I will come to this in a second, are in person only, so they will not be streamed or there will be no online attendees. For all talk presenters, please make sure that you upload your slides at best the day before. That would be very helpful for us via the upload link that we shared with you. And come to test in the morning or on the coffee break before your session. Please come to test it here so that we can make sure everything works smoothly. Flash to poster presenters, I'll come to this also in a second. If you have a poster, haven't had the chance to upload a Flash Talk slide, you have still the opportunity to do so. Just use the upload link we provided, and then you can present a Flash Talk. And here are all these links. Yeah. The schedule, I think you saw this miniature text on this slide, but it's actually not so hard. It's basically always the same setup, right? So we always have plenum talks, followed by Flash Talks, plenum talks, and then some social activity in the evening. And on Tuesday to Wednesday, we have the breakout sessions, which are not happening in this room, but are essentially happening in the seminar rooms around us. The Flash Talks, which are starting here immediately after the session, are the first ones, and then we have some Flash Talks on the Tuesday after in the coffee break, and we have some on the Wednesday. And this is essentially the current lineup for this, so please find your name there. If you are in lists here on the left-hand side, then we will ask you afterwards, after this first session, to come and sort of like come down and then present in this order. We will essentially display the slides, and you have 1 minute to present your poster. Tuesday is here and Wednesday is here. And if you haven't had the chance to send in your poster Flash Talk, please do so optimally today so that we can order them correctly. Then we have these exciting breakout sessions. That is an integral part of the Rocky World's in-person meeting series because we believe that the field, we aim that the conference evolves together with the field. And so we give the participants the chance to actually actively shape the conference by proposing these breakout sessions and then do some activity which is not supposed to be a plenum talk session, another plenum talk session in those breakout rooms. And this is just on this side and on this side. And we have 4 on each day, and I will not going to read those, but essentially they are across all the themes that are happening and that we see in the talks and posters in this week. This will be organized by Amy Bonzo and Olli Schottel, and once we get there tomorrow, they will explain in more detail how this goes. But what you can do right now is already think about on which day you want to go or join which breakout session that will make it much faster and facilitate everything tomorrow. We have social activities going on throughout the week. We will start today with a welcome, not a barrel, a borrel is it supposed to be. Yeah, it's basically an aperitif, okay? 17:30 to 7 or something like this. On Tuesday, and it will be advertised on the specific days, on Tuesday we have a very nice pub quiz organized by Rob Spararen and Mara Attia at Café de Tuta. Please come around 8 to 8:30. We will start with the pub quiz at 8:30. And I think it's a very nice social activity, so please join us all. On Wednesday, we have the formal official conference dinner happening at the NOC. I will give more instructions on how to get there on Wednesday. It's at the top of the forum, Groningen. In principle, you need to have signed up to this. If there's a last-minute decision you want to join or you don't want to join, please talk to us. On Thursday, what also belongs to Rocky Worlds is a karaoke night. And I encourage you all to come and see the LOC and SOC sing. Of course, everybody, and in case the SOC didn't know, that is part of the, like the duty of a SOC member and LOC member of the Rocky Worlds Conference Series. So you can see all of them sing on Thursday. So please join us, and you will get more instructions then. Oh, and one thing is, someone suggested that if you go over time with your talk, the amount of minutes you go over, you have to sing. So we'll see. All right. Before I get to the code of conduct, actually, before I forget it, some people have their luggage actually and put it into this room, and there's some luggage over there at the registration. For safety reasons, we moved all of that to the room 58, which you can find if you go here. So if you deposited luggage in this room or over there, then you will find it in 58. So please get your coats and laptop bags and luggage in 58 afterwards. We all want to be nice to each other, and we want to ensure that this is a very welcoming experience for everybody. So I will summarize this in that you please, throughout the conference, behave professionally and behave welcoming to each other and respect each other, essentially. Do not put down others and try to make this a welcoming, diverse experience for everybody. You can read out the code of conduct in our website, and there you will also find, in case an event happens that you do not appreciate, you would want to talk to somebody or would reach out to somebody, you can find information there. Essentially, you can reach out to any member of the LOC or SOC at any time, or you can write to a specific email, and we do not necessarily, you can remain anonymous when doing so. Yeah, before I finish, a very quick word now to our funders, without whom really the conference wouldn't have been possible in this way. Of course, the two biggest sponsors here are in particular the University of Groningen. We can use these rooms for free, and also the Kaptein Astronomical Institute provided a substantial amount of administrative support for this. And the Space Research Organization Netherlands put in a substantial amount of additional funding to enable us to support several early career researchers and underrepresented researchers, which made it possible for them to attend this conference. In this respect, additionally, the Netherlands Platform for Planetary Science also enabled us funding, and the Dutch Research Council, NVO, also spent a substantial amount of money on supporting this conference. In addition to those organizations, I want to in particular thank Michiel Min and Floris van der Tak and Nienke van der Marel, who helped a lot in organizing all those contributions and actually get this funding. So let's thank them all together for making this meeting possible. That's it. Yes. So thank you, everybody, for listening to this. We really look very much forward to this week. And if you have any questions or anything, any suggestions at all times, please reach out to us. And now what I'm looking forward is to a really exciting conference. And what we will do now is we will start with the very first session, which will be chaired by Quentin Changea.
Thank you, Tim. I think I can use this one, no? No. I think you need to get mic'd. Just yes. Yep. Let me try first if it works.
Yes.
Is how you can use yourself if you want to. But,
Okay.
by default, it's on the microphone is here.
Okay.
It might not be.
Sounds
very
sounds very loud.
Oh,
Loud
okay.
talker. Yeah. I think it'll be
That should be
You have to swap it completely. What does it say?
You have to drag it.
Yeah, just
I think you have to drag, yeah. Oh,
Hmm.
no, it's
doesn't want to get through. Oops. Sorry.
not.
Thank you. All right.
Okay.
All right. We needed the bus to be here. This computer is a bit problematic. Okay, welcome. It's very nice to be here. We're going to start with the first science session on atmospheres. And our first speaker or keynote speaker will be Hannah Diamond-Lowe. She's an assistant astronomer at Space Telescope. She has done extensive work on the characterization of small planets from space and ground telescopes. She's also the PI of the Hot Rock survey, which will observe 9 objects with JWST, and she will give us a keynote talk entitled An Overview of Rocky Exoplanet Atmospheres, Past, Present, and Future. Please take it away.
All right, thank you. You can hear me? Yes. It is a real honor to open up this conference. Thank you for having me. This is certainly not long enough to give an entire overview of the past, present, and future of rocky exoplanet atmospheres, but I'm going to hit some highlights that I hope you will like. Let's see if it works. Okay, so first we want to contextualize rocky exoplanet atmospheres by looking first at, of course, the whole rocky or the whole exoplanet sample, and we're going to focus on our favorite rocky exoplanets. So this is the obligatory figure of all the exoplanets we have detected so far. It is over 6,000 confirmed exoplanets to date. And they're arranged here in planet mass as a function of orbital semi-major axis, so how far the planet is from its own host star. There's many sort of features to point out here, but I think the most obvious one is that where we have detected the bulk of our exoplanets does not cover the parameter space where the solar system planets reside. This is not because we don't think planets exist over here. This is a detection bias. As astronomers, we like to categorize things. So here are our big, broad categories of exoplanets. So hot Jupiters, these are, Jupiter mass planets orbiting very close to their host stars. They're hot. Warmer, cooler Jupiters, more Jupiter analogs that are probably younger, sub-Neptunes, and all the way down here are our rocky worlds. And what is amazing about this, to even have this conference, is we actually have planets in this area of parameter space. This was not always true. So aligning how we want to look at rocky exoplanet atmospheres, we have to first actually detect those rocky exoplanets. And I think this is one of the most sort of fundamental past lessons we can learn. So now these planets are arranged, all 6,000 of them, on a cumulative count as a function of when they were discovered. So you can see a kind of trickle in since the first detections, and now all the way up here over 6,000. And the major workhorse of exoplanet detection, especially if we're thinking about small planets, is the Kepler space mission. Kepler launched in 2009. Its prime mission was to stare at a single patch of sky and detect planets there via the transit method, where the planet passes in front of its host star. Kepler did get an extended mission, but one of its reaction wheels failed in 2013, meaning that it only had this sort of K2 extension where instead of pointing at that single patch of sky, it kind of drifted along the ecliptic, but still made many exoplanet detections. And indeed, even though it retired officially in 2018, Kepler has detected over 3,000 of the confirmed planets that we know about. That's more than half of the planets we know about come from Kepler, which is not bad for a mission that ceased its prime operations over a decade ago. when you have this kind of statistical mission where you're looking at a single patch of sky in the same way for many years, you can do real statistics. And in this way, exoplanets can fulfill this promise of, while we will never be able to measure or do follow-up observations of these exoplanets the same way we can for planets in the solar system, we have the power of numbers. And that means that you can make a histogram like this based on the Kepler observations. I think it's amazing to be the first talk and already someone's shown a figure that I have here. So Kepler, and with some help with ground-based observatories and measuring distances with Gaia, produced this histogram. We have the number of exoplanets per star for relatively short orbital periods as a function of planet size. And what you can see here is that most planets are smaller than about the radius of Neptune. And you also have this interesting bimodal distribution where you have some rocky planets and then maybe some sub-Neptunes that have retained some hydrogen helium in their atmospheres. But the big takeaway here is that small planets are vastly more abundant than large planets in the galaxy. And this is not something we could have learned just by studying the solar system, where we have 4 rocky planets and 4 giant planets. We would have never been able to derive this histogram. So this is exoplanets kind of fulfilling that promise of statistics over in-depth characterization. Now, we're here to think about rocky exoplanet atmospheres, and unfortunately, even though we know these planets are abundant, most of the rocky exoplanets in Kepler are too far away for us to do any kind of atmospheric follow-up. For that, you need to look at planets much closer by, and for this we have the TESS mission, the Transiting Exoplanet Survey Satellite. So this is Kepler. This is the field of view in Cygnus, and it kind of detected planets along this galactic spiral arm. These are too far away, and so TESS is looking for the closest planets orbiting the nearest, brightest stars. And these are the planets that really allow us to even have this conference today. So this brings us to the present, where we actually want to search for rocky planet atmospheres. We have to start by what stars these planets orbit. So this is the so-called M-dwarf opportunity. Just saying that a rocky planet orbiting a small, cool M-dwarf star is going to produce a relatively large transit and radial velocity signal, easier to detect, easier to characterize. There's also a bonus, there's many M-dwarfs. M-dwarfs make up about 75% of stars in the solar neighborhood. So there's many opportunities to find planets and study them. Contrast this with a sun-like star. They are larger, more massive. The same planet would produce a much, much smaller signal. So more difficult to detect, much more difficult to characterize, and there's actually not as many nearby. But as you may know, M-dwarfs also have a drawback. They are more active on longer timescales than their solar counterparts. They're also cool enough that there is actually water in an M-dwarf spectrum. This becomes a problem if you might be looking for water in a planet orbiting an M-dwarf. Because it's really fun to look at big stellar prominences. This is an image, this is an artist's impression from the Keck Institute for Space Studies report. And it's demonstrating that this magnetic activity, these prominences, maybe a coronal mass ejection, might be very dangerous for an atmosphere orbiting a little rocky planet very close to that star. And so this leads us to the question, do rocky planet atmospheres even survive their M-dwarf hosts? But this is kind of an open question. And how do you answer it without just sort of checking a lot of your planets? And so this enters a concept called the cosmic shoreline that has become a very popular concept against which people write JWST proposals. And this is basically showing that if you measure some cumulative high energy, so X-ray and extreme UV flux, as a function, that a planet receives, as a function of its escape velocity, which is a proxy for how well a planet can hold on to an atmosphere, you can sort of make this drawn by eye line in parameter space called the cosmic shoreline, which is saying that things that receive more high energy radiation and have lower escape velocities might be less likely to hold on to an atmosphere, like Mercury. Planets that receive relatively less high energy radiation and have higher escape velocities can hold on to an atmosphere, like Earth or Venus. But crucially, what I really want to drive home here is this cosmic shoreline is purely derived from the solar system. It works for the solar system, and every other dot on here is a rocky planet around an M dwarf. And we have no idea if this line actually holds for these systems. We also don't know as much about the history of M dwarfs, so there should be pretty large error bars, especially in the y direction on this figure. But this is a framework. I guess we can ask the question, not just do rocky planets have atmospheres if they orbit M dwarfs, but does this cosmic shoreline actually apply to M dwarf rocky planets? So this brings us to how we're actually going to try to answer this question. And to do that, we actually want to try to detect rocky exoplanet atmospheres. And so there's sort of three main ways we do this. These are not the only ways. These are sort of the main highlights. One is the primary eclipse or the transit. This allows you to measure the planet size. When done in spectroscopy, you can also measure starlight as it filters through the planet's atmosphere and try to detect the atmosphere and its constituents in that way. The secondary eclipse, often done in thermal emission, is when you measure the planet's thermal day-side radiation as it passes behind its host star. And then you have the phase curve, where you just watch the whole thing. We're going to start with transits. These have been the main workhorse of exoplanet detection and characterization for many years, so it's a good place to start. This is what a transit with JWST looks like. This is the rocky planet GJ486b. You can see here the exquisite precision with which JWST is able to measure the transit itself in broadband. And it is so precise that if you smear out this transit as a function of wavelength, you can actually see this in this kind of heat map here. And this allows you to create a transmission spectrum. So you're measuring this transit depth as a function of wavelength, so these sort of smaller wavelength bins. So here, the black points with error bars are the data, and the colorful lines are the forward models that the authors are comparing to this data. I will say at the top, these data are consistent with a flat line. That is this dashed gray line here. But what's interesting about this paper is that they also suggested that maybe if you look at the blue water line, this also presents a pretty decent fit to the data. So is there water in this rocky exoplanet? Or is it just stellar activity? So these authors did a nice job of doing a slightly more in-depth analysis. This is the same data. The y-axis has just been expanded. And indeed, they can fit a pure water atmosphere to the data, and you get a pretty decent fit. But the point is that these data are equally well fit by a completely airless planet and a star that has unocculted star spots that are cool and have water in them. And there's no way they can differentiate this. I'm not going to get a chance to talk about it, but subsequent data shows that probably this top scenario is more likely. We don't think this planet has a thick water atmosphere. But this is not the only time we've seen this. This is just a few, sort of a smattering of examples of how stellar contamination is hindering our ability to search for exoplanet atmospheres in transit. So I would say the work that is going on currently involves trying to mitigate this M dwarf contamination on transmission spectra. This is an active area of research, and we don't have the answer yet, but it is not an intractable problem. So for instance, you can try to do a better job at measuring star spot coverage as these M dwarfs rotate. Now, this is doable if you have long-term stable photometric monitoring. And so maybe this is something we might want to try to get for some of our M dwarf hosts to try to pull out their star spot coverage as a function of their rotation period. Another thing we need to do, and that we are actively working on, is trying to better model the actual spectrum from the M dwarf. This becomes a problem as you get to these cooler M dwarf stars. You know, we get pretty good stellar models for solar type stars. So when you get to M dwarfs, there's actually some cloud opacity in the stellar atmosphere. And we want to improve the molecular opacity. So what is actually in this M dwarf photosphere? So this is an example from a recent paper by Isha Iyer trying to improve on these M dwarf models. If you can better model your star, you can better pull out the signal coming from the planet or even the planet's atmosphere. These are also important, these M dwarf models, for the next way we want to try to detect exoplanet atmospheres, and that is in phase curves and secondary eclipse, focusing on thermal emission, so farther into the infrared. This is one of the first papers to do this for a rocky planet. So here you have a full phase curve, and these of course give the most information because you are watching the planet as it goes all the way around its star. And you can measure the relative flux of that planet as a function of its orbital phase. So orbital phase 0.5, this is where the secondary eclipse or occultation happens. The transits are over here at phase 0 and phase 1. They're very deep, they're off the figure. And if we make the assumption, this is a key assumption, that the planet is tidally locked in this 1-to-1 synchronous rotation, this means the planet always presents its same face to its host star in the same way that the moon always presents the same face to the Earth. You can fit these data points with a phase curve model. And you are looking for two things if you are curious if this planet has an atmosphere. One would be the offset between the peak brightness and when this secondary eclipse happens. So if this planet has no atmosphere and it's tidally locked and its same face is getting blasted and blasted with radiation from its host star, that energy has really nowhere to go. It's just going to heat up that permanent day side. If that planet has an atmosphere, that atmosphere might be able to actually move or advect some of that incoming stellar energy from the substellar point to the cooler night side of the planet. So we don't see that here, so this planet is consistent with not having a substantial atmosphere. The other thing you can look for to corroborate this is actually how deep this occultation is, so this maximum flux that you are reaching. And similarly, if the planet day side is very hot, nothing to move that energy coming in from the star away from the substellar point, you would get a very deep secondary eclipse. If an atmosphere was there, able to cool the day side, you might measure something a little lower. So the phase curve gives us both pieces of these information, but phase curves are expensive. We cannot observe a phase curve for every rocky exoplanet that we might want to, because this planet, which has a pretty short orbital period, I think it's like 13 hours. Some planets, have orbital periods of a couple of days. So some you're looking at 50, 60 hours just to get a single phase curve. So we want to make our observations a little more efficient so we can hit more targets. And that we are going to do by focusing on the secondary eclipse. So just the part of the planet's orbit where it is about to go behind the star, and then it goes behind the star, and then you see it pop back out at the end. And what you're seeing beforehand is light from the star plus planet system, and then you are measuring how much fraction of that light was coming from the planet's day side relative to the star. And if you make that measurement, you can then compare it to some models that tell you that the deepest eclipse you can get would correspond to a sort of bare rock, no atmosphere model. Alternatively, if this planet has an atmosphere, you might see something a little lower. And key to these kinds of observations is this carbon dioxide bonus that you get at 15 microns. This is to say there is a very well-measured and very deep absorption feature by carbon dioxide at 15 microns. We know this because we have carbon dioxide in our own atmosphere. We've measured this very well, and so we can put it in our models. Luckily, the MIRI instrument on JWST has a photometric band right at 15 microns. And this is going to be a big advantage, or we're going to take this big advantage to try to detect atmospheres on rocky planets. But this leads us to the question, what kind of rocky exoplanet atmospheres are we detecting? And there's a point I want to make here that's very important. So this is from a paper by Sebastian Ziba, who is here today, showing this is very nice measured eclipse depth of TRAPPIST-1c. And then this measurement comes over here. This is the planet-to-star flux ratio, and we're going to compare it to some models. But this isn't the important point. This is. So the models that we can compare to in a sort of grid are these surface pressure on this y-axis. So you're going from 0.01 to 100 bars as a function of how much carbon dioxide is in the atmosphere. So going from about 1 part per million to a pure CO2 atmosphere. The numbers and the color of the boxes correspond to the confidence with which the authors are ruling out this type of atmosphere. As you can see pretty clearly off the bat that these carbon dioxide-rich, high surface pressure atmospheres are the ones that are most easily ruled out. But I want to put this in context of how we maybe think about atmospheres growing up here on Earth. which is that the atmospheres that they are really addressing are Venus-like atmospheres. Venus has almost pure CO2 atmosphere and about 100 bars of surface pressure. Not very nice for us to live on, but easier for us to detect if this atmosphere existed in a rocky exoplanet. The Earth also has carbon dioxide in our atmosphere, more than we would like. And that parameter space at about 1 bar is right around here. And you can see that if we knew nothing else about Earth's atmosphere, but that it had 1 bar of surface pressure with about 200 to 400 ppm of CO2, you could maybe just say something about that, but you're really not reaching that detection level. Even more interestingly is to think about Mars. We know Mars has an atmosphere. That's why it's hard to land things on the surface. You have to worry about a lot of heat friction. But Mars's atmosphere, while dominant in CO2, has a very low surface pressure, about 6 millibars. And so as you can see, sort of based on these trends, these data, though exquisite, are not able to address a Martian-like atmosphere. But we would not consider Mars to be an airless planet. So this is important to keep in mind. So when we're talking about detecting rocky exoplanet atmospheres, a lot of the time we are thinking about atmospheres in this regime, because this is what we have access to with our measurements today. Okay, so back to our cosmic shoreline. Does this apply to M-dwarf rocky planets? Well, we have done some investigation, and I'll say at the top that so far we have not detected definitive evidence for a 1 to 10 bar, at least, carbon dioxide dominated atmosphere. But we've done a lot of looking and a lot of learning in trying to investigate these rocky exoplanet atmospheres. So here is, I don't even think this is a comprehensive list anymore, but these are some individual investigations for these planets circled in purple. And since I am the PI of the Hot Rock Survey, I also have to include the Hot Rock Survey here that add these sort of red circled planets. And if you'll notice, all of these planets fall on this, atmosphere less likely side of the solar system cosmic shoreline. This is because these are not statistical surveys. We are not leveraging as much as we can the large numbers of exoplanets relative to solar system planets. These are low-hanging fruit, opportunistic investigations, some of the earliest we've done with JWST. Now, we still are working with a pretty small sample here, but in order to try to push into this area of parameter space, you need a lot more telescope time. And so for that, we have the Rocky Worlds Director's Discretionary Time Survey. So I'm not the PI of this survey. I help implement it. This is time that the Space Telescope Director has given to try to make a push into these more difficult targets, right? The cooler targets take a lot longer to observe. So these are the kind of gold points that have been on the figure secretly the whole time. And this is going to take 500 hours of JWST time to use this same method, this MIRI 15 micron photometry method, to try to look for hints of atmospheres, probably only addressing CO2 dominated 1 to 10 bar atmospheres on these planets. And this is going to be a big push in this direction. I don't have results to show you yet, but you can please check out our website. We have updates all the time. It's going to be very exciting. And I have stickers if you want stickers. Okay. The point of all of this, though, and this is one example of a figure like this, but the point is to try to do actually population level characterization of rocky exoplanet atmospheres. We are getting closer, but we still have a long way to go. So this is actually, this was on the archive a few days ago, I think. And this is comparing the planet's day side to its theoretical maximum as a function of irradiation temperature and trying to see if there's any trends that might be able to be pulled out. You might be curious about these planets down here that look a little more atmospheric. These are extremely, extremely hot. And I'm going to punt that to Joanna Tuskey, who's talking later in this session. Okay, so we wanted to talk a little bit about the future. And I see that there are two things we're going to keep doing and do them more and do them better. And that's more occurrence rates and more characterization. So on the horizon, we have the future of rocky exoplanet occurrence rates, and there's a mission that I think is going to do some really interesting work in this space, no pun intended. And this is the Nancy Grace Roman Space Telescope, which will launch either towards the end of this year or early next year. So this is coming very quickly. This is a 2.5 meter mirror. This is the same size mirror as Hubble. And the optics of Roman mean that it will get a large field of view at spatial resolutions similar to Hubble. This is what that looks like. So here is the HST field of view. Roman's in one shot is about 100 times larger. And Roman will be able to rapidly tile areas of the sky, so it will even more multiply that field of view rather quickly. Now, Roman is not going to operate like HST or JWST. It has these core community surveys that are just going to go. All the data will be public immediately. And of the 3 core surveys, we probably care most about the galactic bulge time domain survey. Time domain, we like time domain, that's how you find transits. And this is going to look towards the galactic bulge just a little bit south of it. And because we have these Hubble-like spatial resolutions, Roman will be able to resolve billions of stars in the galaxy. And so what this might look like is at least 30,000 new transiting exoplanets. Really building on the legacy of Kepler, transiting exoplanets is still easier to detect when they're closer and larger. And Roman will also have a microlensing survey component. If you want to know more about microlensing, you can ask. But this is basically going to give us about 1,000 new planets in this area of parameter space we have never before been able to access for low mass planets. To put this in context of our original figure, Nancy Grace Roman is going to fill in this area of parameter space. And I am so excited to know what the occurrence rates of Earth-like mass planets orbiting at multiple AU is going to look like. We have no idea. Okay. We don't just want to learn more about how many exoplanets or rocky exoplanets are out there. Sorry, I should mention. These, though, of course, will be too far away in the Roman mission for us to do the follow-up. So we have to have other strategies to do the in-depth characterization if we want to actually study atmospheres. One I want to highlight, these are by no means a comprehensive list, but one I want to highlight is the ground-based high-resolution observations that are going to become possible with the ELT, the Extremely Large Telescope. It is being built in Chile. It's going to have a 39-meter segmented mirror. Oh, 10 minutes. That's ages. All right. Excellent. So the ELT, right, this is a super large mirror, and I want to highlight one of the second light instruments that will be on the ELT, which is Andes. This is going to be a high-resolution spectrograph. And I haven't talked about high resolution, but it is going to be a very powerful tool and hopefully will unlock information about rocky exoplanet atmospheres. And this is why. So if you can see this figure up here, this is the water band around actually WIF-C3. And you can see these black sort of points here. That is the low resolution that we are able to get to with our current space missions. So if you're looking for water, you're probably just looking for this broad feature. But if you can dial up that wavelength resolution to over 100,000, you can actually get the true spectral fingerprint of water in your data. And you can try to separate that from the host star's water by virtue of the planet's motion around the star. And this could be a very powerful technique for detecting rocky planet atmospheres. Even farther into the future, we might have the Habitable Worlds Observatory, which will go to space and will use direct imaging, another technique I have not talked a lot in this talk so far. But the point here is that HWO will be able to both detect and characterize rocky planets orbiting sun-like stars. So if this is a little dark, so maybe you can't see. This is a simulation of the solar system where the, sorry. Yeah, is there a light? Okay. It's like ironic because I'm going to talk about how faint the Earth is. Yeah, okay. So very realistic. Yeah, so this is a simulation of the solar system where the light of the star has been blocked by a coronagraph, and by suppressing the stellar lights, you're able to pull out the very, very faint light from an Earth-like planet orbiting nearby. This would probably be in reflected light. To explain how hard this is and why this is not launching in the next year or two, we need to get down to a 10 to the minus 10 flux contrast between the star and the planet. So it's being able to pick out a signal at 1 part in 10 billion. So this technology does not exist yet. People are working on it. But I want to kind of put that in context of what we can already do. So here is that flux ratio from planet to star. You can, with instruments and telescopes you might recognize, HST, JWST, more specialized instruments like Gemini and VLT Sphere, you can get down to flux contrast that allow you to at least detect hot, young planets around stars. The Roman telescope that I mentioned earlier will have a technology chronograph demonstration, and they are hoping to get down somewhere around this level. The ELT will do some direct imaging as well, hopefully down as well to about 10 to the minus 8. But we need to get 2 orders of magnitude lower with the Habitable Worlds Observatory to actually accomplish the kind of detections that will allow you to not only find an Earth-like planet on an Earth-like orbit around a Sun-like star, but also characterize its atmosphere. So that is farther into the future. And the design for habitable worlds is not yet set, and the sort of instruments and how this pyramidal space will look also not yet set, but a huge amount of discovery space potential. Okay, so concluding, rocky planets are abundant. We knew that coming in, but it's still important to remember. Today, currently, we are leveraging this sample of small planets that we have now to try to figure out if these planets around M dwarfs have atmospheres. And remember, we're really focusing on CO2-dominated substantial atmospheres. I didn't get a chance to talk a lot about this, but I hope you took away that M dwarfs are really important to understand if you want to actually understand these rocky planets and their atmospheres. And finally, that future missions are going to continue filling in missing occurrence rates for rocky planets and also provide more sensitivity to rocky planet atmospheres. Thank you.
Amazing. Thank you, Anna. Brilliant. Do we have any questions? See in the middle.
Hi, thanks for the talk, Hannah. You were saying when you were introducing the cosmic shoreline that it was calibrated for the solar system for sun-like stars, but not so much for M dwarfs. What's specific about the calculation of the cosmic shoreline made it only unique to the solar system and sun-like stars and not M dwarfs?
Yeah, and it's not even sun-like stars, it is the sun. So that line is actually drawn by hand. If you populate that parameter space with not just the solar system planets, but also asteroids and minor bodies, moons, that line pretty much holds. We know that for all the objects orbiting the sun, they basically had the same stellar history modulated by their distance to the star. We also know a lot more about the history of the sun, or solar-like stars in this case, in terms of how long they're active, how much activity, and sort of their spin-down rates. For M dwarfs, there's a lot more uncertainty in how long they spent in their saturated high-energy state when they're young. Then they sort of spin down, but at different rates. And the M dwarf class themselves, an earlier M's history is not actually that similar to a later M history, but we kind of just shoved them all on the same graph anyway. So these are a few of the reasons why the cosmic shoreline is a bit shaky to apply to M dwarf systems. Yeah.
Thank you.
Amazing, thanks. I will ask you to say your name when you ask a question. Any other questions? Maybe at the back. And then at the front here.
It's Claire Guimond, the ET Zurich. Thanks for the talk, Hannah. So maybe could you go back to the sensitivity plot where you showed like increasing CO2 and atmospheric pressure? Or maybe it's too far back, but my
No,
question
we can do it. From this
yeah,
one?
this one.
Mm.
So like as you increase CO2, why does the sensitivity go down and then up again?
So this is
Yeah.
increased. Sorry,
For like the low pressures.
here.
Yeah.
So right, so this isn't sensitivity. This is the degree to which the data rule out this
Right.
model. Okay. As you have lower and lower surface pressures, the model atmosphere becomes less efficient. You just get less absorption from the CO2. So you're less able to detect an atmosphere with very little surface pressure, even if it has a lot of CO2.
Right. And then does it matter if you like have a different, any like inert background gas, or is this really specific for oxygen?
I would say oxygen is, this could be another neutral background gas at these wavelengths. Yeah, so the wavelength coverage you have kind of dictates what kind of molecules you are sensitive to. Oxygen here is just kind of a filler for a gas that like we wouldn't know anything about what's happening with oxygen at 15 microns. It's non-reactive out there. It's just kind of a filler. We don't have anything where we could do like line pressure broadening. It's too low resolution for anything like that. So yeah, thanks. But it couldn't be hydrogen, right? Because that would give you a much puffier atmosphere. Yeah.
Thank you. I think we had a question here.
Hi, Hannah. Tom Wilson, University of Warwick. Very nice talk. I was wondering if you could speak a bit more about using UV spectra to disentangle molecular features in planetary atmospheres from stellar activity. You kind of touched upon it a few slides before this, but how can we think about using UV spectra to...
UV spectra.
Yeah.
Ooh. Hang on. Okay, bear with me. I have bonus slides, so we're gonna go all the way through. So UV spectra are interesting. They basically, how far is it?
I can wait, it's fine.
Wow, it keeps going. Okay, yeah, so here, okay, yeah, UV spectra. So there's sort of two things, right? There's these sort of potential for like clouds and water in the stellar photosphere. That's kind of one thing to figure out. UV spectra are interesting because the ultraviolet is really important for reactions that would happen in a planet's atmosphere, like photochemistry or atmospheric mass loss, or the extreme UV is more for atmospheric mass loss. So this is comparing an inactive, quote unquote, inactive M dwarf to a G star. If you sort of normalize to a doesn't have to be the half bubble zone, or normalize to some distance, you see that the M dwarf, which is here in red, has proportionally more high energy flux relative to bolometric than the sun, or than a sun-like star. And this is important because when we're trying to detect rocky planet atmospheres, you're most readily sensitive to what's happening in the upper atmosphere. And this is exactly where the high energy is depositing its energy. So this is kind of a few steps into the future, but if you were to detect an atmosphere on a rocky planet, knowing the UV output of the star is going to help you understand maybe why those molecules are there, or if there is no atmosphere, why there's been so much escape. So you're still getting just a snapshot in time, but it does help. Yeah.
Makes sense. Thanks.
Yeah.
Okay, we have time for a few more questions. I think we have a question here. I didn't see any people at the back asking questions.
Bennett Skinner, McMaster University. I was just asking for hot rocks and rocky worlds. Whenever you were showing the survey for the cosmic shoreline, kind of just what's the selection criteria for those targets? Because it looks kind of random in the two parameters that are shown here. Is there a secret third parameter where it's sensible, or what's the selection criteria?
Yeah. You ready for this ride? Okay. Oh, yes. Can I do this? Did I ruin everything? I just want to be able to like scroll up and up. It's fine. I can just talk. So for the Hot Rock survey, that's like a PI program that I submitted to James Webb. That is just the easiest targets we could fit into a reasonable large program. That was basically, and for the planets had to be rocky and get enough signal to noise. Oh, that's great. Oh yeah, I can do that. I got it. It's over here. That's confusing. So that selection criteria is just easy targets that we could do this for. For rocky worlds, we were trying to both. Am I going in the wrong direction? Ooh, I got it. We were trying to both fit these planets into now a much larger program, so we have a little more leeway here. But we also wanted, the goal was to get a sample that spanned this solar system cosmic shoreline. These two targets here, because you might ask, why didn't we just take all these targets? These two will take will take over half the time, just those two targets. So you're kind of taking selection criteria, trying to make a sample that will answer your question statistically, balancing with just the reality of the amount of hours you have to fit your program into, and that's kind of observing reality. Yeah.
Cool. Any other questions? And maybe I will ask one question. Are we going to detect an atmosphere in the end?
Will we?
Oh, yeah.
Oh, I don't know the future, so. But I will say, I think like the prospect is exciting, and it's also okay if we don't, because that will have also taught us something about our local universe, and that's important too.
Okay, amazing. Is there any question online? I didn't ask online. No questions online. Then let's join and thank one more time Anna. And I think our next speaker is Pierre-Olivier Lagage. Thank you, sir. Yes.
You want the mic back?
Yeah.
I will just attach this here so that it's. All right, so it's maybe better like this. And somehow just in your pocket, it's very comfortable.
All right. Okay, slides okay. Now we have Pierre-Olivier Lagage from the CEA. He will talk about GWST observation of TRAPPIST-1c at 12.8 microns. You have 10 minutes. Please go ahead.
Okay, thank you very much. And it's good to go just after Diana, because it's just following the talk, and a lot have already been said. So, concerning TRAPPIST. So, down to go. Okay, it's not usual. Yeah, it's weird because it's down to know for the others. You have to, not up, down. Okay, just a few words about the TRAPPIST opportunity. So the TRAPPIST system is made of a star and 7 exoplanets. And the star is very small. It's barely bigger than Jupiter, but it's still a star. It's very cold, which is nice for eclipse. And in terms of contrast, it has a very small radius, small mass, and it is nearby, which is also very interesting. The planets are rocky planets, and they have been detected by transit method. And their radius about the size of the Earth, mass also about the Earth's masses. And we can calculate the density so that it is really rocky. And the mass have been calculated by TTV. And the orbital motion varies between 1.5 and 10 days. So that's very good targets. And in addition, there are 3 of these exoplanets which are in the habitable zone, making them very interesting. So we got some GTO time, and we spent some time to observe the first one, the nearest exoplanet to the star, which is TRAPPIST-1b. And to observe it, we make some eclipse observation to have the thermal emission. Diana has just mentioned you that it was one of the techniques to observe if there is an atmosphere or not. And given the temperature of the exoplanet, the best instrument is the mirror instrument. And as already mentioned, so we have chosen to have two filters. One was at 15 micron because of the CO2 feature, large feature. And another one was at 12.8 microns to have the flux at this level without feature, good also. And we have a collaboration with Tom Green, and we spent 5 eclipses to get a good signal over noise at 15 microns. And later on, we had also 5 eclipses at 12.8 microns. And you can see here the result. So you have the wavelength, you have the filter coverage, 12 and 15, and you have the eclipse depth. According to that, there are several possible surface for a bare rock, which can fit the data. So given the high temperature, the absence of CO2 large absorption, we can say that it is a rocky planet. But it is not as simple. And to add in complexity, to determine if you have an atmosphere or a bare rock, we had an alternative models with the 2 points. It was done with Elsa and Mikhail, where you can have, if you have a temperature inversion in the atmosphere, you can have some CO2 in emission instead of in absorption. And in this case, you can have a high point in terms of atmosphere from CO2. It will not be absorption. Following to this 1D calculation, there have been a phase curve saying maybe if you look at the night side, you will have some low flux if it is rocky, because it will be the dark side, not the bright side. So we have this phase curve, 72 hours of observation to have a full phase curve for B and a partial phase curve for the C. And the results are not fully conclusive, because you can have models which also fit this low value for the dark temperature. Dark temperature, you can think that it should be bare rock, but even with the emission in the atmosphere, which is due to hazes which are heated by the star, on the dark side you don't have heating, so you don't have emission, CO2 in emission. But the conclusion, I let you read the conclusion. So it could possess an atmosphere with a thermal inversion and hazes, although this case seems unlikely in phi terms, but unlikely is not well defined, I would say. So, good. Let's go now to 1 point. So TRAPPIST-1c. You have already seen this figure by Sebastian, Laura, and other authors. And you are, again, the wavelength, you have the depth of the eclipse, and you have this point, which can be interpreted with several ways, with some CO2, or, given the uncertainty, as a bare rock. So we decided to also have a 12.8 point. Okay. And so we have a large team. So it was program 5191. So all the people interested in TRAPPIST or having already worked on TRAPPIST have joined this program. And we made 6 data reductions, 6 different data reductions by Taylor, Michael Gillon, Elsa, Bryce Olivier, myself, Sebastian. So for sure, it has been detected. It has been detected at 4.5 sigma. And for sure, the eclipse is high, of the order of 400 ppm. But there are still work needed to fully understand some differences between the models. The differences are between this 440 and higher depth. And we really need, I think it's not only for this observation, but in general for eclipse observation and analysis, we need to assess the uncertainties due to the analysis and to combine the uncertainty you have on the data and the uncertainty on the analyzing. And it has already been seen in other observations of other rocky exoplanets, but what is really weird, one of the 4 eclipses is barely detected. And that's something we don't understand, but that's something to work more. So if I put in the diagram you have seen before, the new point, putting the value of about 440 ppm, you get this time of profile, and it goes in the direction of having a bare rock, but the bare rock is not the only thing which can feed the data. You see in another model with a 0.1 bar of oxygen and 100 ppm of CO2. So we not only look at the data at 12.8 micron, but we also reprocess the data at 15 micron. And we had one more point, one more eclipse, because we had this phase curve observations. And then we got some values somewhat in agreement with Sebastian and Laura, between 360 and 413. So again, some dispersion due to the analysis. And recently, we also find in the literature lower value. So again, there is really a need of better understanding the systematics and better having good uncertainties in the analysis. So what we have started to think is about a new metric to distinguish between various observations. So we notice that for various rock, surface rock, if it is a bare rock, the value in terms of the ratio between 15 and 12.8 micron is relatively constant at a value about 140. And another thing which is interesting with this metric is that it doesn't depend on the absolute flux of TRAPPIST. And in fact, there have been some change recently in terms of flux because of a new calibration. So about 10% of increase in the flux of the planet due to the new calibration. But when you take the ratio, it's just difference between 2 nearby wavelengths, so it's not such important. And at the moment, if we look at possible models, and there are much more, but you can see that you can, with enough sensitivity, enough with small uncertainty, distinguish between bare rock and atmospheric scenario. And I arrive to my conclusion. So for temperate rocky exoplanet, only James Webb can characterize them, and more observation are really needed and discussion about systematics. Thank you very much.
Thank you. Perfect timing. Do we have any question for Pierre-Olivier? Yeah, I see a question here.
Bennett Skinner, McMaster University. Do you have any preliminary speculation as to why you might have not detected it for one eclipse?
No, that's really weird, and no, it's something we are trying to figure out, but no idea at the moment. And statistically, we never know for eclipse, but it's really out. So that's another reason to have more eclipse, more observations.
Okay. Another question? Questions online? So maybe I'll ask one. What is the next step then for TRAPPIST 1b and 1c? What should we do?
I would like more observations. More eclipse.
Okay, let's thank Pierre-Olivier one more time.
And more, yeah.
And our next speaker is Joanna Teske from Carnegie. She's here. And while she is setting up, I will give the name of the talk, A Volatile Envelope on an Ultra-Hot Super-Earth. Okay, Joanna.
Yes, down.
Straight. Down works? Does this work? Yes. Okay, excellent. Then you can take it away.
Much. It's wonderful to see everyone. Thanks to the first two speakers of this session for kicking us off. My name's Johanna, and I'm going to talk about a rocky world that we think has a somewhat surprising volatile envelope. This is based on JWST Cycle 2 data. And what I'm showing here is an artist's conception of this planet, TOI 561b, which if you think about how do you make an image of a lava world that you think has an atmosphere on top? Like how do you convey that there might be lava underneath some thick envelope? So this was fun to work with Space Telescope on this image. This is done in collaboration with a large team of people, including a few folks who are here this week. Emma, who's on the LOC and has a talk on Thursday. Alex has a poster on this data set. And really my talk is kind of just an advertisement for his poster. So he has all the juicy stuff. And then of course, Tim, thank you for organizing this meeting. In this talk, I'm mostly gonna speak about the emission spectrum that we've measured from this planet, but we have a full phase curve. So as Hannah mentioned, there's a lot of information in that type of data set. And so I'll show a little bit of a sneak peek at some of the phase curve results, which are being prepared by both Alex and Samuel, who is an undergraduate student working with Lisa. And so we hope those results will be submitted soon. Okay, so TOI 561b is a seemingly anomalous planet. It's down here in this mass radius diagram, which is a little bit outdated, but gives you an idea of just where it's located. This is an ultra short period planet. So it has an orbital period of about 10.5 hours. And so that means, again, we think it's tightly locked to its host star, which is a G9, kind of slightly cooler than the sun star. And ultra short period planets have these very, very, as you might expect, highly rated, very, very hot day sides, hot enough to be above the melting point of pure rock. Most of them are sort of in this part of the parameter space of mass radius. So many of them have kind of Earth-like bulk densities, but there's a subset of them, which includes TOI 561b, which are anomalously underdense. And in particular, 55 Cancri E is another one of these, which I think we'll hear about also later this week. But TOI 561b is on the smaller side, right? It's in that first peak of the double peaked histogram that we've seen a few times of the radius distribution of planets. And so it's even a little bit weirder that it has this anomalous low density. Another thing that sets this planet apart is that it orbits a thick disk star. And so that's a star that is in the thick disk of the Milky Way, you know, up above the thin disk where our sun sits. That means it's old, so kind of twice the age of our sun, and that it has a different composition, drastically different composition than our sun. So it's low in iron and higher in alpha elements, the stars. And so we might think that the planet formed in that type of environment. And so there's lots of cool things that make this planet stand out. I'm also mostly interested in population level conclusions, but this planet was just so weird that it was worth spending some time studying in detail. And so for this program, we're interested in, does this planet have an atmosphere? And does that explain its low density? And so, like I said, I'm going to be going over the emission spectrum. And so this is JWST near spec G395H data. So it's just in 3 to 5 microns. It's kind of a small snapshot in wavelength space. And I'm going to walk you through this diagram. I'm just going to step through and add some components. For the sake of time, I'm not going to go over how we got the kind of all these different reductions of the emission spectrum. I agree that it's really important for these small planet data sets to do different reductions, try out different pipelines, make different assumptions about how you're fitting the data and how you're propagating your errors through. So that's what this plot represents, kind of different assumptions about those things. I'll point out that the red points have an error inflation term, and there's not red points here just because the error inflation term was less than 1. So they would correspond to just the Eureka points. Anyway, the first thing that we saw was that the emission spectrum is inconsistent with a bare rock. Now, this bare rock model has a 0 bond albedo, and we have seen at least 1 or 2 examples in literature already of planets that have potentially have very high albedo surfaces. And so is that a possibility for this planet? Yeah, this is not a to scale diagram, but I'm trying to draw a cartoon of like a rocky planet with a shiny surface here. Okay, gotta speed up. We think that's probably not likely. The surface of this planet would be so hot that rock would be vaporizing off of the surface. And so that would cause at least a partial rock vapor atmosphere. And at these temperatures, that atmosphere would be optically thick due to strong opacities in this wavelength region. And so the emission spectrum would be set by the atmosphere rather than the reflective surface. So we think that's not what's going on. We also tested a thin rock vapor atmosphere in comparison to the emission data and find that is also inconsistent for the most part with the spectrum. And it's really important that yeah, so we think it's not a thin rock vapor atmosphere. One thing that we still think is maybe possible is something like very reflective clouds in the atmosphere, although there's a lot of uncertainties about how clouds could exist in such an atmosphere. Would they be on the day side? Could they even be providing the cooling effect that we need to produce the low emission flux? And importantly, that would still be at odds with this low bulk density of the planet, which is only about 70% that of the Earth. And so we think right now that the best explanation is that this planet has this volatile-rich atmosphere. And so here, I haven't done as extensive tests like Sebastian did in his paper, although we're planning that for a follow-up paper. This is just a representative set of volatile compositions that we plotted to show were, potentially consistent with the emission spectrum. So that's all based on the emission data. I have a little bit of a sneak peek of this full phase curve analysis that I wanted to show. So this is work by Samuel. And the first point is that, so here is the eclipse, and then as Hannah showed in her talk, the transmission or the transit of the planet, And so what this is showing is the night side temperature of the planet has this long tail, and this is separated into NRS1, which is the bluer channel, and the redder channel in this instrument. So day side, very hot, we know that. There's this tail for the night side, which goes all the way down to 0. So potentially a cold night side, but really if there's something, data are favoring a cool or warm, something like that, atmosphere, particularly the NRS2 data, the redder data. And we're really needing a high albedo to match the observations. Now, like I said, the day side of this planet is so hot, it would be, magma, it's rock that's vaporizing. And there have been some studies in literature suggesting that quenched glass or molten silicates really are not going to have such a high albedo. And so this is further evidence that something is causing this planet to be reflective that's not at its surface. And so again, we're thinking something like exotic clouds, but we have a lot more modeling work to do with that. And like I said, you should really go check out Alex's poster. This has a lot more juicy details about the phase curve analysis. Oh, and one thing I didn't mention, I don't have a plot of it, but if you sort of squint, you can see that maybe we're also measuring an offset in the peak of the emission here versus right when the planet is passing behind the star, which is another evidence of something circulating heat. Okay, so we think, again, atmosphere may be highly reflective. And in our first paper, we're suggesting that this could be due to secondary outgassing or secondary atmosphere from outgassing on the planet. Again, this is a very old star, and so we're not suggesting the planet held on to a primary atmosphere for this whole time. We think it's something that has volatiles that have been able to have been stored in the magma and then outgassed later. But still, how would this planet hold on to even a secondary atmosphere, right, for such a long time? Is it something with magnetic fields is always like the answer in the back pocket? Did it have a late delivery of volatile material? Did this planet arrive late at its current orbit? That is a possibility, but even in models that represent this for ultra short period planets, it would still probably be sitting at like 2-day orbital period versus 0.44 days. So that's still pretty close to the host star and hard to explain an atmosphere. So this is an open question, but taking a step back, maybe it's not super surprising that we're finding this for this planet, because similar to a plot that Hannah showed, it seems like we're starting to see these very hot planets have observed brightness temperatures that are cooler than their irradiation temperatures. And so maybe these planets are hanging on to atmospheres. And just, again, putting up the cosmic shoreline plot. Again, Hannah showed this in the context of M dwarfs. TOI 561b is not an M dwarf, but it's still sitting in this part of the parameter space where, based on this, this line, we think planets wouldn't have atmospheres, and yet it does, or we think it does. And so it sort of challenges that conception, at least of doing this in a 2-dimensional space, and maybe is something we need to revisit in the context of secondary outgassed atmospheres. So my time is up. With that, I will stop and take questions.
Thank you so much, John. I'm so sorry, I've been tasked to distribute karaoke song. That's why I want to really make sure we go on time. Okay, we have 2 questions, maybe those 2 first, and here. Yeah.
Hi, Sebastian Sievers, Center for Astrophysics. Can you maybe say something about the star? Which kind of star is it? And do you see any evidence for activity in the phase curve maybe also? And did you compare the extracted stellar spectrum to like the models?
Yeah, so for the second part of your question, yes, we did compare we have high resolution stellar spectra of this star. It's a G9 dwarf. And so we compare that, and I mean, the near spec data are very low resolution, but it seems to match okay based on what we have from the optical data. And in the phase curve, what I showed, that modeling does include a GP for low-level granulation signal. And so we're actually working a little bit with Dan Huber on that, but it's about what you would expect in terms of the parameters of that fit for a G9 dwarf star.
Okay, there was a question in the middle here. There are many questions.
Hello, Sarah Edinburgh. Great talk. I was curious also kind of along those lines, is there any room for errors in our understanding of the star that might link to maybe this planet is a bit bigger and than we think it is, or kind of what errors exist and where in our errors could this maybe be in terms of mass and radius that could maybe explain this?
Yeah, so kind of getting to the basic parameters of the star and how that would influence the derived parameters of the planet. The star, I don't think so. I mean, the star is very old, and so it's quiet, right? It's a pretty well-behaved star. The RVs don't show lots of jitter or anything like that. I will say that the mass of this planet did move around a little bit in the literature. That was actually part of the background motivation for the JNUST proposal. But as more rate of velocity data have been added, the mass points have sort of converged into still a low mass, or sorry. Anyway, the radius is high given the mass. And so I don't think there's something weird going on there, particularly from the stellar perspective.
But two more quick questions, one here, one here.
Okay. Hello? Yeah. Okay. Hannah Devereux, Space Telescope. In the phase curve you showed, you mentioned briefly that there did seem to be an offset in the secondary eclipse from the peak thermal emission.
Right.
But it looked to be in the opposite direction on NRS1 and NRS2. Okay. Is that real? And if so, are you thinking about the TP profile that might constrain? Are we seeing deeper motion of the atmosphere in one direction versus something else in the upper atmosphere?
The short answer is yes, we're thinking about that. I'm not sure that the offset difference between NRS1 and NRS2 is significant, but by eye, it's suggestive for sure.
Cool.
I will ask Christopher Monaghan to come get prepped while we are having the last questions.
Sit on. Okay. Hi, Johanna. This is Laura Kreidberg from MPIA. Congrats on this beautiful result. I have a question also about the phase curve. So it looks, at least by my eye, that for the NRS2 phase curve, you have a pretty strong detection of night side emission, but not on NRS1. Can that be explained by, say, CO2 absorption that is stronger in one detector or another? Yeah, where do you stand with the interpretation?
Yeah, it's still very much in prep work. And so I don't want to be too speculative. I will say though, that something I forgot to mention was the break between NRS1 and NRS2 is right here. And so this point these are all on NRS2. So there's not some offset weirdness going on there. And so we're very interested in why there's low flux here, which I think is related to what you're asking about.
Great stuff. Thank you.
Thank you. Let's thank you one more time. And our next and last speaker of this session is Christopher Monaghan from the Trottier Institute in Canada. He has a very long talk title, which is Uniform Reinterpretation of Existing Secondary Eclipses of Rocky Planets and the Impact of Stellar and Orbital Uncertainties on Compositional Constraints. And we're getting set up with the slides now.
Thanks so much. Works? Yes. Okay. Awesome.
Okay, take it away.
All right. Can you hear me? Awesome. All right. Hello, everyone. My name is Christopher Monaghan. I'm a second year's master's student at the University de Montréal. And today I'm going to be presenting this concept of the model uncertainty, which we actually heard a little bit from one of the questions previously, but it's this sort of ever-present source of uncertainty in the models we generate, particularly for emission spectra, that no one's really looked at least in a very in-depth manner. So today I'm hopefully going to convince you that it's important and that we should start accounting for it in future observations. So earlier we heard about things like the DDT and the hot rock survey. We have a ton of really exciting observations with secondary eclipse observations with the James Webb Space Telescope coming up shortly, particularly with the DDT, which has 500 hours of dedicated James Webb Space Telescope time to observing with MIRI the secondary eclipse depths of a number of different rocky exoplanets. And the idea behind this is to probe whether or not these planets have atmospheres and to constrain their potential compositions. So it's important that our method of analysis is robust enough to really get the most out of these observations. And generally right now, with these secondary eclipse observations, we oftentimes just compare our eclipse depths to a number of different forward models. So we compare our measured eclipse depth to a number of different bare rock or atmospheric spectra, just to see what our planet could be consistent with. More recently, we've shifted towards, in addition to these models, this calculation of this R ratio, which we saw earlier, which is this brightness temperature ratio that represents the day-side temperature that we measure to some theoretical maximum of a dark bare rock. So if we detect something that's similar to R equals 1, we probably have something that's more consistent with a dark bare rock. If we get something a lot lower, that might be consistent with an atmosphere, and we can begin more sort of compositional analyses thereafter. So like I said, there's been a ton of more recent observations with the James Webb Space Telescope. And one sort of example I found in particular was GJ367b, which has a really well-constrained eclipse depth of about 79 plus or minus 4 parts per million with MIRI LRS observations. And from this sort of sampling of its R ratio, we can see that it's probably consistent with a dark bare rock to a pretty robust degree. However, if we now account for this mystery thing called the model uncertainty, our constraint for R becomes much less significant, much less robust, and all of a sudden we can have anything from about 0.9 to 1.3, which brings into question what the composition of GJ367b is for any of these planets. Now I skipped ahead. I'm cheating. So what is model uncertainty in the first place, and why is it so large in particular for GJ367b, and how does it impact our compositional constraints from other exoplanets with secondary eclipse observations? So it's actually very simple. It all boils down to our precision of what our model parameters are. So if you go to like the NASA exoplanet archive or anything like that, you always have these like plus or minus error bars for the planet and stellar parameters. When we make emission spectrum models, however, we oftentimes just take these median results and ignore the plus or minus ratio that we have. This is ignoring the distribution of potential values these parameters can have, and therefore is, I guess, in a way biasing the models that you're generating to something that might be more likely, but again, we don't necessarily know for certain because of these statistical distributions. So what I did to investigate this is actually quite simple. I just reanalyzed G367b as a dark bare rock by generating a number of new emission spectra by simply sampling the relevant astrophysical parameters instead of taking these median results. So the parameters we choose to sample are simply the ones that impact the eclipse depth as shown here. So of course the RPRS ratio, as well as anything that impacts the flux density of your planetary surface and your stellar surface. So we choose to model things that are oftentimes used in stellar grids like Sphinx or Phoenix. So the effective stellar temperature, the metallicity, the C/O ratio, and the log G value. We also want to scale this so it matches the approximate luminosity that we measure of these stars. So we also scale the stellar radius and observed luminosity, and of course, the 7 major axis of the planet. These are also quite easy to, I guess, choose as they're directly constrained via both transit observations and general stellar modeling when you constrain the parameters of your star in the first place. So if we did all this one time for a dark bare rock, so I'm going to skip over the math because it's a little bit boring, but it's effectively just radiative transfer balance, you could get things that hopefully this shows up well on the projector here. You could get a stellar flux density that maybe looks like that, planetary flux density that looks like that, and an eclipse depth model that looks like that. But again, this is just for one single model. And what we want to do is resample this again and again to sort of explore this posterior distribution space of potential GJ367b models that could be consistent with that as a dark bare rock. And as you see, we're slowly filling out this parameter space for the measured brightness temperature, the measured eclipse depth, and MIRI LRS. And we're also filling out this small posterior distribution of potential consistent stellar models, planetary flux models, and eclipse depths. And it's this distribution of models that could be consistent with GJ367b as a dark bare rock that I've been referring to as the model uncertainty. So if we let this run for long enough, we'll eventually have explored the significant amount of space in order to calculate this model uncertainty and begin comparing this to our observations. So we can also look at the sources of the model uncertainty by looking at what happens if we sample each parameter individually rather than sampling them all at once. And if we do that, we can see that each parameter has a pretty significant effect on the measured eclipse depths that we generate. So even if we had a well-constrained star, for example, if we ignore the radius of the star, its luminosity, and the more intricate parameters of its metallicity, and we simply sampled for RPRS or AP, we can still generate a large degree of variation between these bare rock models, which indicates that we really need these robust, precise model parameters when we generate these model spectra of emission spectra. So like I said before, we want to also reanalyze the suite of existing observations of rocky exoplanets. And we're going to do this with this R ratio to start off. So we saw a plot similar to this before with this R ratio as a function of the irradiation temperature. And these are just all of the observed results for rocky exoplanets, or approximately rocky exoplanets. Gets a little bit funky with some of these lava super Earths, alongside their observed uncertainty. So purely just from the eclipse depths of these planets, these are the error bars we have for this R ratio. If we now add the model uncertainty, all of a sudden, all of our constraints become far worse. For some of these, it's not super significant, depending on the model precision that we have, or in some cases, depending on our observational uncertainty, which for things like Spitzer is oftentimes quite large. However, for some of these more recent observations, GJ367b, LTT1445 AB, and a number of other observations, suddenly our model uncertainty is effectively making it impossible to generate strong compositional constraints on these planets. If we look at specific model spectra, for example, we have a lot of overlap between different bare rock models that we generate, for example, LTT1445AB or GJ1132b. So distinguishing between these models is effectively impossible given the combination of observational uncertainty and model uncertainty that we now have to account for. The issue especially is that with more observations of the eclipse, we can make these error bars for these bin points a lot smaller, but the model uncertainty can only be reduced by further refining the parameters that we have of our planet. And like I've mentioned before, this doesn't just affect things like bare rocks, this also impacts atmospheres. So when we're trying to detect an atmosphere, there could be overlap between different bare rock surfaces and atmospheric models that make it difficult to really refine your observations and get strong compositional constraints for your planets. So no one wants to repeat the same 2000 model generation that I did because it's incredibly computationally inefficient. So what I did is I sort of sampled the candidate DDT targets. There was a list of about 80 before they chose their final selection of 9, or I think their final selection of 9. And I redid that sort of 2000 model generation of all those candidate planets as a dark bare rock. And as it turns out, you can make these approximately linear relations between some sort of error summation. So all the sources of uncertainty that you're throwing into your model generation, you can roughly add the sort of like percentage error of those. And you can plot those and generate these linear relations that give you these really easy to derive MX plus B models that allow you to approximate your model uncertainty. So even if you have a really complex atmosphere, if you know where your uncertainty is coming from, there should be ways to derive that to generate a more intricate mathematical calculation of the model uncertainty rather than having to brute force it like I did previously. So just to sort of summarize, this model uncertainty is simple in theory, but it has this huge impact on our compositional constraints that I think we need to start accounting for, especially in light of this upcoming Rocky Worlds DDT. It's important that we be more honest with the results that we're generating, especially because there's a ton of other effects that can modify the robustness of our compositional constraints. Things like thermal beaming and surface grain size and regolith on bare rock surfaces, for example, can all drastically affect your emission spectra. So even just the most simple way of sort of propagating your uncertainty with this model uncertainty method is important to account for when we start making these, start trying to detect atmospheres on these rocky worlds from emission spectra. So anyway, I'm going to end it off here. Please stay tuned for our AJ paper. It goes a lot more into detail about what we did here, and I'll be happy to take any questions now or at any point throughout the conference. Thank you all so much.
Thank you so much, Christopher. There are many questions. We have time for a few, maybe. I will start on this side because I've given a lot of questions on this side at the previous talk. So. Yeah.
Hi, thanks. Great talk. So as a
Please state your name.
sorry, my name is Nienke van der Merwel from Leiden Observatory. And so my expertise is actually protoplanetary disks and planet formation. So exoplanets is always like a bit of a new thing for me. So I'm curious with all the issues that there clearly are with modeling exoplanet atmospheres. I feel like the models are just too complicated. You're trying to fit too many things for both the data as well as the uncertainty in all the other parameters that you have. And I think in disk studies, people have, at least in the past, were very pragmatic with this. So they just simplified the models. They knew they were not physical, but at least you could identify trends. Is that something that should be considered for exoplanets as well? And how would we do that?
That's a really good question. Actually, so this paper did start off as a simple reanalysis of the existing observations, but instead of using a uniform temperature black body for a dark bare rock, we started using like this sort of integrative method to give you like a temperature gradient on the day side. So the models we're using are still pretty simple. I had a whole extra slide that just showed how complicated these models could get, and at that point, then it would be useless to even talk about this. But the idea is that whether you're using like a black body spectrum or something like this, where you have like what is effectively a number of smaller black bodies of varying temperatures, you're still going to have this model uncertainty regardless of how complicated your model starts off as. That's why I just chose like these bare rocks, for example, because these are effectively all the same model with a slightly different wavelength dependent albedo. So, or not that, what? There we go. So yeah, for regardless of the model you're using, regardless of how complex it is, you're still going to have like these sort of mystery error bars that whether or not you're accounting for everything that could modulate like how accurate it is really up to what you're actually accounting for. So.
Thank you. I think next question is here.
Well, Brandon Parkoy from UChicago. Nice talk. So when we're trying to derive these R values, so the dayside temperature divided by the theoretical maximum, we do typically use like Gaussian priors on things like the stellar temperature and the different orbital parameters. So when we're deriving this, we do try to account for uncertainties in stellar and orbital parameters. I did notice, could you go back to your end slide, actually?
End slide?
Yeah. It seems like you might be sampling a couple of parameters that are dependent on each other. Like, for example, the stellar radius and the stellar temperature theoretically determine the luminosity. So I'm wondering if that's why you're retrieving larger errors on this ratio than we were previously, because we do try to account for uncertainties in these types of parameters.
Yeah, so that's where it gets a little complicated. I kind of just threw in the parameters that we're using. It gets a little bit difficult to choose the parameters. Inherently, what we're trying to do with like modulating both the effective stellar temperature and all the other things is that your spectral energy distribution shape from like these spectral grids that you're using is affected by like these four parameters here, while the actual like energy balance is affected by R star and L star. So those, I'm not super keen on how like the actual parameters are chosen. I think it's just like a number of flux observations with different filters that they then compare to these like really highly like computationally complex like stellar models. But the idea behind it was that we don't have this strong confidence as to the exact, like if we let this run for a bit, the exact shape of the spectral energy distribution, both at short wavelengths and at long wavelengths, is sort of difficult to constrain. So that was the idea behind sampling those four parameters, as if you ignore the R star and L star, this height wouldn't change all that much, but the actual shape of it would. But of course, by sampling the star itself, then you have the issue of, well, sometimes we have these photometric measurements, which sometimes isn't consistent with our observations or like the models that we generate with the spectral energy distribution. It's a whole issue, which is why I think we need to start like actually measuring the star with like a pretty high resolution in order to generate these models in the first place. Because for these dark bare rocks, most of that flux is either re-radiated or as a black body or reflected from the star itself. So having strong like accurate knowledge of the star is important. And for a lot of these planets, we don't, even if we have a pretty well-constrained luminosity or something like that. So that was the idea behind sampling all these intricate stellar parameters, was purely just to make the shape of this more complex than we know. Because we wouldn't actually know like the exact way it bends at all wavelengths.
Okay, thanks. Yeah, we can chat a bit later.
For sure.
Yeah, I would like to give 3 more questions, so please be brief in when you ask your question and answer the questions. There was one here, and then one here, and I think one here. Yeah, that doesn't matter. We'll do all of them, but yeah.
sort of following from Brandon's question, you're sampling just from sort of like the reported results that are on, for example, like NASA exoplanet archive. Those results, if done well or done comprehensively, are from a sort of global fit that has been sampling a broad range of parameter space, and those results actually have some are related to each other from covariance matrix. What strikes me is what you might actually want to do is instead of producing samples based on sort of best median plus or minus error bar, to actually go to those posteriors and sample from them directly. Have you like tried to do this or contacted some of these teams to ask for their MCMC posteriors or dynamic posteriors?
That's a great thing I should do. That's sort of like another issue as well, is that a lot of these like plus or minus error bars also are reporting like different percentile, like quantile significances. So yeah, they're not all Gaussian either. So for this, the way that we were doing it here, I was assuming just Gaussian using those plus or minus error bars. But even like, for example, like even the parameters that you generate for the same planet sometimes are vastly different in terms of like how much they agree. So for example, there were some models for LTT 1445AB that has slightly different, I think this was RPRS. And whether or not you chose the blue model or the yellow model for your parameters, all of a sudden you either have something that's effectively a dark bare rock or maybe like a really strong atmospheric detection. So there's already like now issues just between like the choosing of the parameters in the first place. Now, again, this is just assuming that Gaussian sampling, which maybe not Gaussian, but like the, yeah, so like the sort of sampling from a normal distribution rather. But yeah, I think that ended up being the issue. I talked with the author of that paper just to see why they chose which one. But like might be other cases where this is not the case. Like there were other things like I do this whole or the candidate DDT target thing. And I think some of the planets here are in that reanalysis I perform, and they disagree because they have different parameters that are selected from. So it's this really sort of big issue that if I was doing like what I wanted to do was like a much larger survey, then I would be in a pickle because then I have so many different samples I need to choose from. But I think it would be more robust to actually go in and select those individual like final samples they have.
Unfortunately, I will not be able to
Sorry.
give the last two questions. So maybe you can go at the break and ask the two questions later.
Sure.
I'm sorry about this. We have to move to the flash talk now. Can I get the flash talk? You've seen also your, please, let's all join and thank Christopher.
Thank you.
And for the flash talks, you also saw your name at the flash talk for the first days. Those that have their name and their flash talk now, please queue on this side.
Yeah. Yeah, I think that will be easier now. Yeah. Maybe you can. Yeah.
So you mentioned, but you guys know to mention the poster competition. That's all. Or you will mention it. Are you talking now, or?
I will give my flash talk today. Yeah.
Oh yeah, okay. It's just there's a slide that says there is a poster competition. Please do it.
When at the beginning?
If you do the poster QR code is in the next slide. Yeah.
So you can,
So
if it's not done at the end, you can you buy people.
I'll be in the queue.
Okay, so you can just do it. When this goes to your.
I don't hold the competition. It's fine. I think it's fine if you don't. Please get it. Don't say anything.
Perfect.
QR code is private copy.
Okay. Perfect.
Hold on.
Do you have your
a big line of people.
You have your person now? Are you on one of those names? Okay, then you can do it. Up to you. Do you want to do it? Okay.
All right.
All right.
This conference doesn't only feature a selection of wonderful talks. We also have a selection of wonderful posters that you can all enjoy and admire during the coffee break. But first, we would like to give you a small sample of the posters that are on display here. Now, before we actually start with the flash talks, just quickly want to say, we also have a poster competition. So if there's any poster out there that really strikes you as excellent and deserving of a wonderful prize, then please scan this QR code, which you can also find in the hallway, and put in the name of the person who made this poster And then at the end of the week, we will announce the winners. One quick note, LOC members are excluded from this competition. So if the person who made this poster is one of these red cords, then you're not allowed to vote for them. I'm sorry. But then without further ado, I would like to start off with the first person. You have 1 minute each, and we will cut you off. Otherwise, you will have to sing some songs during the karaoke. So it's maybe better to just cut you off. Okay, go.
Hi, everyone. I'm Madeline Broom. I'm a final year PhD student at Santa Cruz, where I spent the past 6 years working on WINDY, which is an open source 1D atmospheric escape code with metals. And when we've stuck metals into these, we've been able to explore interesting relations in super Earth parameter space, including the classic fact that energy limited mass loss rate calculated at RP is going to severely overestimate your mass loss when it comes to pure hydrogen helium atmospheres. Also, when we add metals, we're able to see some trends in mass loss, where mass loss rates decrease more steeply with metallicity for low escape velocity or low surface gravity planets. And last but not least, that metals can completely suppress outflows. In particular, I've looked at preliminary CO2 atmospheres and seen that these shut off mass loss entirely. So if you want to hear more about that, my poster is over by the coffee. Thanks.
I am Judy Wan from the University of Bristol, and I at this time got a poster on our most updated research on the aluminum mechanism chronology. And here are our most updated results. We've using a new collection method that separate the olivines, and then we can measure the nucleosynthetic magnesium in the aluminum-free phases. Then we can use the canonical model to calculate the deficit age. And from our results, the barred olivines actually form the latest in the sequence, and then type 2 chondrule formed in the middle, and type 1 formed the earliest within the first million year after the CAI formations. And this actually matches with the LELA dating results. We've also done 2-point isochrons. I think we haven't been done before using the olivine and bulk, because typically people use the aluminum-rich phases to do this. So this time we get the highest precision, and this result also matches with our magnesium deficit age. And my page is at the door. Sorry, the second one at the door. So number 80.
And if you taste it, then you pretty much just taste tequila and orange juice. But if you cheat slightly, and if you pour in some grenadine, and then quickly, then it tastes a lot sweeter, because you're tasting the grenadine before it's had a chance to sink to the bottom. If you want to find out how that has anything at all to do with exoplanets, why it's not, I promise, just to leave the day through, then please come check out my poster or come and chat with me.
Hi, I'm Leonie Janssen from Leiden University. And so our poster is about variability. Basically, that's what you see on the slide. On the left-hand side, you have a planet which is super hot, molten, and which is outgassing some stuff. And on the other side, you see a planet that is colder and cloudy. And basically, we're trying to figure out if the same planet, through its lifetime, can go through both changes at quite short timescales, actually. That's the wrong way around. Yeah, so we're trying to answer how cloud formation could lead to such variability. And we're also looking into how this would affect emission spectroscopy, and if the timescales are such that it could potentially explain the variability we see on 55 concrete. So come check out the poster. Yeah, it's exciting.
temperatures have more temperatures, and then it's the chemical evolution work where we show that the late explosion of small stars enrich the galaxy iron our planet at the time. And I always have a chance that one of the developers in Agricia, and I got the notification as I walked up here that the stickers are so stickers of breaking down. Thanks, my poster is over.
Yeah, hello everyone. Oh, it's already the results. Okay, I had some animations, but it's still it's not working. So we are studying the very early phases of the planet formation, starting from the molecular collapse of the cloud. There was an animation here. So the first result is that the dust inside the molecular cloud, which is collapsing and forming the protoplanetary disk, is starting to grow already during the collapse, which is very important, and it's growing to a few millimeters, even centimeters. So we have pebbles already in a forming disk. And what's also important, what we see, but you cannot see here, but you can see on a poster, so it's more intriguing. You will be able to see a lot of sedimentation in the disk that is forming very early. So we are simulating until 12,000 years after the disk formation, and you have a lot of pebbles sedimented in the midplane of the disk, which means we can form planets already very early phases. So if you are interested, the poster is near the entrance. Thank you.
Hello, this is Shohei Aoki from University of Tokyo. So in this poster, we focus on Mars, which is a dry and dusty world. So in this poster, we essentially investigate how the transit spectrum look like if there is a Mars-like exoplanet. For that, we use actual solar radiation measurement taken by Mars orbiters. And in the transit spectrum, we identify two interesting aspects. So one is seasonal variation, the temporal variation of the CO2 features, which is driven by the dust. It's driven by the planet dusty cycle of Mars. And the second interesting aspect is a very strong feature at 3.1 microns, which is due to very small submicron size water ice clouds in the mesosphere of Mars. And if I'm happy that if we can talk more in front of my poster, if it is there. Thank you so much.
So, hello, my name is Xuecheng Yang, and I'm from ETH Zurich. So, if anyone study magma oceans and atmosphere, very likely you need to assume that they are in chemical equilibrium. But recently, there are some papers arguing that this is not a good assumption because they think the volatile transport in the magma ocean is not an efficient process. And we study the same problem, and we conclude that we have the opposite conclusion. So, what is really happening is that you have to split the problem into bulk transport and boundary layer transport. The bulk transport is fast. The boundary layer transport is very slow. But in reality, the boundary layer doesn't exist. So forget about it. If you're interested in the details, you're welcome to come to our poster, which is right next to the place where you get a coffee. Thank you.
Okay, imagine the year is 2030, whatever, and we just found that TRAPPIST-1e has an atmosphere, and it's got water and oxygen and all this stuff. It is Earth-like. The media loses their mind, but not you and I, because we know that there's a big difference between if we're talking about like 1% or 2% CO2 in terms of the surface conditions of that planet. But I mean, this kind of discovery is something that we hope should be able to happen in the relatively near future, right? That we make this kind of discovery. And when that happens, we're going to have to confront whether our telescopes and our techniques can actually distinguish between small chemical differences at the precession that we will need to actually say something about habitability. Can we do that? Well, my poster is just one big plot, and the situation is so much worse than you think it is. I'm right by the coffee. Thank you so much.
All right, just quickly going to insert myself here. But to keep a planet habitable, it's important to have a recycling of crustal material back into the mantle and then maybe back out through volcanism, which on Earth tries a lot of climate feedback mechanisms. But this is highly dependent on the crustal properties of these planets. Like some planets that have a crust that's way too light. So you get planets a little bit like here, where all the crust is stuck on the surface, cannot subduct, and you're locked out of these climate feedback mechanisms. Or maybe the crust is actually too thick and or too dense and will actually accumulate on the bottom of your mantle, never to be re-entrained in the mantle again in order to, and you will also be locked out of these climate feedback mechanisms. So what I do is I take a look at expected planet compositions based on stellar abundances, and I try to derive some crustal properties and mainly crustal density contrast with the surrounding mantle rocks. And if you'd like to see more, please come to my poster. It's somewhere in the coffee room. I actually don't know where, but we'll figure it out.
Hi everyone, Alexandre Branco. I'm a first-year PhD student in the University of Porto. Well, my work has focused on these two individuals, HSO and HNO. We currently don't know how these two molecules absorb in the UV visible range, and they are being included in photochemical modeling of Earth-like atmospheres with anoxic environments. So my work was to change the cross-section prescriptions that we currently use for proxy molecules of these two and see whether they have any implications in our prediction of abundance profiles in these anoxic atmospheres around sun-like stars or M-type dwarfs, kind of. So the consequences of these weren't known until now, but they are kind of being figured out by this sensitivity test that we're running. And the reward, if anyone finds cross-sections for any of these two molecules, would be more reliable photochemistry modeling of Earth-like atmospheres eventually. Thank you.
Hello, I'm Vincent Savignac, the third-year PhD student at UC San Diego, and I've been studying the formation of the Earth. Specifically, I've been studying how a volatile reservoir in the deep mantle coming from the solar nebula can be used to trace back the formation processes of the Earth. And with formation models, how we can constrain the properties of the Earth as it emerged in the disk. And we conclude that we can use light noble gases, that helium and neon, to probe early gas accretion in the nebula, and heavier noble gases like argon, krypton, and xenon to probe solid accretion processes. And if you'd like to learn more about it, please come by my poster. I'm on the right here.
Hello everyone, I am Chandan Sahu and I'm presenting my work on effect of composition variation on thermal evolution of rocky planets. We all have an idea of how planets form from the protoplanetary disk towards a completely formed planet. However, the change in its mineralogy and its effects on the thermal history is not very well known. For example, we do not know how does the composition affect the mantle solidus, the convective flow and the viscosity of the rocky planet, the thermal evolution, as well as the melt production and volcanism rate, which is pretty interesting to be observed on the surface. And we model on Earth's mantle, we see that the majority of minerals is olivine and pyroxene. So we model the end members, phosphorite and pyroxene, and observe some effects on the thermal evolution. So to know more, please visit my poster. Thank you.
Hi, everybody. I'm Tad. Yes, just like the 90s rock band. I have been working for the past 7 years to figure out whether hurricanes can occur on rocky exoplanets orbiting M-dwarfs with some Earth scientists. And thanks to the hard work of a couple graduate students, especially Valeria Garcia and Cole Smith, that ran high-resolution simulations, we do think that they can form. And then lastly, I want to mention that Toby Hammond is a graduate student at Purdue who could not be here, and we wrote a really, I think, interesting paper, and I highlighted in the poster, so please come by to support Toby and these other great students. Thank you.
Hi, my name is Sophia Vaughan. I'm from the Max Planck Institute of Astronomy. We know emission and transmission spectra are good, but I like reflection spectra. And they provide, they're very cool. They provide a lot of information on planets, especially rocky ones. So for example, Earth-like planets, they're very unlikely to transit. They're cold. So some of our key biomarkers are going to be in the reflection spectrum. They can tell us about cloud properties by measuring the line widths of the spectrum at high spectral resolution. And if you get a phase curve, you can see little bumps in it due to scattering phenomena due to liquids such as water, which is very cool. And so I've been sort of working on a timeline of these kind of reflected light observations Starting with today with the VLT, looking at the strange world of LTT 9779b in reflection and constraining its cloud properties. Moving to whether we can characterize one of the first Earth-like, potentially Earth-like planets with the ELT in the near future, and even further with the Habitable Worlds Observatory to see if we can show those little bumps due to rainbows. Thank you.
Hi everyone, I'm Lieke, a second-year master student at Kaptein Institute, and my poster focuses on which terrestrial protoplanets we can detect with METIS. As the title already indicates, METIS brings direct imaging of terrestrial protoplanets and the atmosphere is within reach. It focuses on infrared because that's where the emission of the planet peaks, and we focus specifically on protoplanets for the insight into planet formation. And the way we evaluate the performance of the instruments is with contrast curves, where any detectable planet falls above the curve and anything that's undetectable below the curve. And these are part of the results that we got, where we see that it strongly depends on the spectral type and distance, planet temperature and radius, and also the observing wavelengths, which planets we can, protoplanets we can and cannot see. And we also focus a bit on the multi-planet systems. So if you would like to know more, then I hope to see you at poster board 76.
Hi all, I'm Zach Burr. I'm a first-year PhD student at ETH Zurich working on precursor science for the LIFE mission. LIFE, the Large Interferometer for Exoplanets, is a future space telescope mission with the goal of characterizing rocky planets in the mid-infrared. So let's imagine that in 20 years from now, this mission is flying and we observe an Earth twin and we get a really beautiful looking spectrum like this. Of course, we would like to know what this planet is made of. So we run our atmospheric retrievals, and the mid-infrared is really great for constraining a lot of key gases in Earth's atmosphere, like water, CO2, methane. But we miss out on two of the really big ones, which is N2 and O2, because they have no absorption features whatsoever in this range. And determining what the bulk gas of the planet is really important for understanding what is going on at that planet. So we would like to know, is there a way that we can determine just with what we can measure with life, what the bulk gas of this planet must be? And if you'd like to know how we are tackling this problem, then you can come talk to me at my poster. Thank you.
Hello, everyone. Greg here from Team Heischen in Cambridge. Please don't boo. If you're not a fan of Heischens, I know you're out there, this poster is still for you. And if you are a fan of Heischens or you don't know what they are, then this poster is definitely for you. So we're introducing an ecological model. It's very basic. It has some bacteria, different types of bacteria that you can see on the right-hand side. And we have viruses as well in the model. We run a few different scenarios related to tidal locked planets and planets with different orbital periods. Sometimes the bacteria die a lot, sometimes they survive and flourish, and sometimes the viruses don't survive either. If you'd like to know more, come and chat. Thanks.
Hi, I'm Andrea, and my poster is about the thermal evolution of non-synchronous lava worlds. As you can see on the animation on the top, we usually assume that lava worlds rotate tidally locked to their stars. So that yellow magma ocean is always facing the star. But what happens to the thermal evolution of the magma ocean if this is a non-synchronous rotation? So for example, a 2-to-1, as you can see on the animation on the bottom. Well, what we get is two different final states. One is it keeps the magma ocean liquid, and the other one is completely solidified. If you want to know more, my poster is at the board 17, and come talk to me if you have a postdoc position.
All right, thank you all for being so on time. Unfortunately, we don't have many karaoke songs, it seems. Okay, I won't keep you much longer from the coffee break. It's right behind me, and we will start here again at 4. Thank you.
Off here.
Test. Okay, must be much closer. Switch it off. So just trying to get a good sound. So you have 10 minutes plus 2 minutes questions. Yeah. Do you want me to give you 2 minutes or 5 minutes? 2 minutes. 2 minutes. So I'll give you a sign when it's 2 minutes, and I'll give you a sign when you should stop. Okay. That's good. Otherwise, I'm singing, right? Otherwise, you're singing. You don't want to do that. You can also just go on if you want to start singing, right? Right. All right. I don't know if that's close enough. Working? Turn it on. Oh, it is. Yep. Thank you.
Maybe at the end of the session, announce the time for this it starts tomorrow again. We'll not get together session. We'll start tomorrow again at 9.
The time for the borough is directly after the session.
Yeah, I mean,
It's here.
just tell them it's like
It's here?
yeah. Tell everybody like it's all.
And then say that tomorrow we started. Yeah, sure. Yeah. So if everybody could take a seat, please, then we can start with more fascinating talks. Right. Okay. So welcome back. We have now a session with several talks, with 6 different talks. We start with a talk from Jonas Byron on building a high-temperature spectral library to interpret lava worlds. So, floor is yours.
Thank you very much. Everybody can hear me well? All right, good. Thank you for this opportunity. It's an amazing conference. I'm really excited about all the science happening this week and what you have to show. Among the very interesting talk, I hope mine would be interesting too. This project was made possible by the Carl Sagan Institute and funded by a NASA grant and in collaboration with 2 amazing labs in France. And this is about building a high temperature spectral library to interpret lava world. So lava world, yes, those fascinating, scorching, scary planets. What are they made of? What is it to look at the surface of those planets? What is it to stand on it? That's what we are trying to understand today. And this review paper shows the many different phases of those exoplanets. Do they have an atmosphere or maybe not? Do they have a magma ocean on one side and maybe the other, and not the other side? Do we have a basal magma ocean? Do we have volcanic features? And so on and so on. So what would the surface of those worlds look like? Is it like smooth and gentle lava flowing, or like you can see at the beginning of the video? Or is it more like abrupt and eruptive and with a lot of hot gassing like you can see at the end of the video? And that's really important because lava worlds are actually the beginning of our own story, right? The early Earth was a lava world. And the beginning of any exoplanet, rocky exoplanet, is also a lava world. And when you think about it, the cooling and the crystallization of a magma ocean leads to the formation of the core, the formation of the crust and the mantle, the initiation of the tectonic plate, but also the onset of the creation of an atmosphere that we know of. All of these are the building block of life, right? And so that's why it's really interesting. However, no lava world in the solar system, but we have detected a lot of them outside the solar system. And that was 15 years ago that we started to observe those planets. And 15 years ago, Professor Lisa Keltenegger and Professor Yamila Miguel had this question: what are the atmosphere of those hot rocky worlds made of? We couldn't understand. That was only a theoretical question at the time. It took only 15 years to get to the point where we can slowly measure those atmospheric composition. And that's a review paper by Laura Kreibert, here present, and that looks at the different atmospheres of 10 hot rocky worlds. That's amazing results. And what you can see, however, is that there are not many absorption features in those spectra, which makes the interpretation of those data very difficult and complicated. And many people have tried, many publications came with this, like you can see on the right-hand side of the slides, an example with 55 concrete E. And so, because it's so difficult to interpret the atmosphere of those planets, maybe we can update our telescope, or maybe we can renew our models or do something like that. But a point that I really appreciate in that review paper is that they suggested, what if we don't look at the transmission spectroscopy, but instead look at the emission spectroscopy? And when you think about emission spectroscopy, that means you need to look at the radiative properties of the surface. And for that, we don't have many understanding. We need experts on this topic. And I'm sure many of you are in this room. Don't ask that guy. But when you think about it, the radiative properties of a surface is the capacity of that object to physically emit heat radiation. And that's the definition of the spectral emissivity. And that's what I am expert on. Just a quick rundown on the state of the art of emissivity. The spectral emissivity is usually considered constant. We usually those model with a bare rock composition, right? With a given value for that emissivity. Or we can sometimes use reflectivity data from different rocks composition, but it's mostly used at low temperature using those reflectivity data. And we have many examples of this, right? Only a few laboratory data exists on the measurements of emissivity at high temperature, but sometimes they lack the physical meaning of those data. So when you think about it, when you're modeling, for instance, if you have a wrong estimation of those emissivities, it might lead to a wrong interpretation in terms of temperature or composition of your lava well. You get it. The accuracy of your observation depends on the parameters such as the emissivity. And so we have a lot of work to do. And for that, I went to the field and collected different rocks, volcanic rocks, natural rocks from all over the world, but also collected some meteorite as well. And we brought that back to the lab. In the lab, we apply different methods to prepare the samples. So we can either core the rock itself and then make a glass of it. We can cut it, slice it, and polish it up to the point where we have a satisfactory sample that we can put in the setup to measure the emissivity. And so that's what I did most of my time last year. Here is the setup in question. You have two infrared spectrometers on both sides of the sample chamber. The sample chamber contains the black body and the samples. Both are measured simultaneously in the same spectral, thermal, and optical condition as the mathematical equation of spectral emissivity requires it. And the sample is heated by a CO2 laser, meaning it's not touching the samples itself, but we can reach 2500 K with that. And what you can see live is pretty much a molten planet, but in the lab. And so we did that work for many different compositions. Here are a few preliminary results, so I'm asking you kindly to not take pictures. So here is a broad range of the different compositions we have studied. This is a task diagram. That's how we classify volcanic rock on Earth. And like I said, we have a bunch of different compositions from the Earth, but also meteorites. And those results look like this. The emissivity for different samples, here are 6 of them. And what you can see clearly is that emissivity cannot be considered constant, right? It's changing all over the place. If you take different composition, different emissivity. If you take different temperature, the color bar, different emissivity. If you take different spectral ranges, you have different emissivity as well. And so the way it can be helpful into what you are doing as astronomers can be multiple different ways. One of the ways that we are currently working is using those laboratory data to build a theoretical framework to understand a moon formation event. If we take the moon formation event and split it in different phases, most of them are actually lava world phases, and we can use that to try to interpret and understand the detectability of such event. Of course, it's going to depend on the intensity of your signal, and some phases might be more detectable than others. But what really the laboratory work can show you here is that we can differentiate it between different thermal regimes in those phases. Is the phase pretty hot or cold? And that's something we can probably detect. In terms of composition, we can go one step further. We have so many different composition measures that we can also differentiate those compositions. But that might be easier at low temperature than high temperature, simply by the fact that we have lower or less absorption features at high temperature, and so that's less chances to be detectable, right? So that's one idea that we have, but also, of course, we can also measure using those data, we can interpret better the observation you are making. We can improve the models you are using. So like I said at the beginning of the video, and that has been presented earlier, instead of a bare rock, what if we use an actual natural composition, but at high temperature? And that might change the results. That might be interesting to look into that. Another way we can use those spectral emissivity data is helping in the construction material for lunar regolith, for instance. This is a 3D printing station with molten rock, and we need the emissivity data to understand that so that we can have more space exploration. And so with that, I'm going to leave my conclusion remarks here. I hope that the key message, you got it. Laboratory work is important, but multidisciplinary work altogether is even more important. And if you are really into lava world and you want to explore the frontiers into modeling, observing, and experimenting with these exoplanets, please come to the session I'm hosting on Thursday, 3:30. Thank you for your question, and happy Rocky World 4.
Thank you very much for this very interesting talk. I see several questions. Maybe I can try to get a mic over there.
Hi, Francesca. I was wondering what's the uncertainty on your measure of the emissivity, and what's the sampling size of the spectrometer versus the size of the CO2 laser you're using to heat your 1 centimeter sample?
Very, very good question. I like that you ask. So in terms of size, the sample I showed you are 10 millimeters in diameter, but the laser heating is, let me show you this. This one might be better. So this is 10 millimeters in diameter, but the laser heating spot is actually smaller than that. It's like 6 millimeters, but the measuring spot we have is actually 2 millimeters. So that allows us to have the same thermal condition. It's homogeneous in temperature overall. What is really important too is the thickness of your sample. And the thickness is, I mean, emissivity is dependent on the thickness, right? But we realize, I mean, there is a constraint between what you can do in the lab, the size that you need. If I'm taking a sample that is too small, the sample might, melt and then flow in the setup. You don't want to destroy your setup. So you need a sample that is thick enough so that it can hold the temperature and the structure of the sample. So we are creating this pool of magmas inside the sample that is temperature homogeneous. And that's from which we are measuring the spectral emissivity. Does that answer your question? Yes. Thank you.
One very quick additional question. Yeah, I saw you have your hand up.
Very quickly point out your question about the sample collection.
Yes.
When you are taking this water rock and putting it into what I presume is water,
yeah,
does that have any effect on the composition?
No. The idea is that we quench the sample. And so it becomes glass. And so you crystallize the structure as in which it was, you preserve the structure as in which it has been collected. So it's mostly dependent on the eruptive style you're going to have, stuff like that. But that's cool because for exoplanets, we might have different eruptive processes, right? That's what we are trying to understand. So we're trying to reach out more than just one composition.
Okay, thanks.
Thank you very much. Yep.
Okay.
Thanks.
So we're going to continue with the influence of the surface with Maurice Stenthoff on the influence of surface roughness on the phase curve of airless planets.
Right. Thank you very much. My name is Moritz Stenthoff. Can you hear me? Right. My name is Moritz Stenthoff. I'm a PhD student at TU Dortmund University. And today I'm going to talk a little bit about work we're doing on the solar system and how this might apply to exoplanets and why it could be useful. I want to thank our collaborators as well. So many airless rocky bodies in the solar system, like the Moon, Mercury, and many asteroids, are covered by a rough layer of regolith. And this, the roughness of this layer heavily influences the reflected and emitted radiance of these bodies. And today we're going to look at how does this affect the phase curves and why is it important. And usually we apply disk resolved models. So we take surface elements, for example, of a sphere here, and there could be two ways to model this. One is a smooth model where the received flux of the surface is governed by the bolometric albedo, and the emitted flux is governed by the bolometric emissivity. However, this cannot accurately explain measurements in the solar system. So instead, we use an advanced roughness model by my colleague Kai Wolfert, where we further divide each surface element into facets and use a fractal surface. And for this fractal surface, we have all these different facets that scatter light each other, heat each other. And so the emission of one surface element is not a single Planck function anymore, not a black body, but a superposition of many Planck functions of different temperatures. And there are two noticeable effects which come from this. And here we have this fractal surface. And at the top, you see a heat map of the fractal surface, depending on the incidence angle of the sun or the star. And you see with increasing incidence angle, certain parts of the surface are hotter in red, and certain parts are in shadow, shown here in blue. And yeah, if we look now from the same direction as the sun comes, so I equals E, same direction, those shadows are not actually visible to the observer, and we mostly see the hotter parts of the surface. Which means that for low incidence angle and emission angles, there's pretty much no difference between a smooth model and a rough model. But the higher the incidence angle gets, there's quite a large difference in radiance when temperature between the rough and the smooth model. And the second case is shadowing, where we look from the opposite direction than the star and the light is coming from. And we start to see more of these shadows and less of the hotter regions. And yeah, this leads to the opposite case. Still no change for low incidence and emission angles, but for high incidence and emission angles, the rough models actually predicts slightly smaller emission than the smooth model, although it's not quite as strong of an effect. And here's one recent example. This is data from the METIS instrument, a thermal infrared spectrometer measuring from 7 to 14 micrometers on board Bepi Colombo, which had its 5th flyby in December of 2024. And here's some of the disk resolved data in black, or in red, sorry. And there's our model applied or computed with different roughness values. And as you can see, we need quite a high roughness to actually fit these measurements. So a smooth model could not explain these measurements. How does this apply to the phase curve? If you now go ahead and integrate these disk resolved measurements over the area, we can see here, for example, a model phase curve for the moon, where we have 4 low phase angles. We see the limb of the moon or the planet, and we get this thermal beaming effect quite strongly. And for high phase angles, we have the opposite. We have this shadowing effect here. And now we can go ahead and maybe apply this in a forward modeling step to different exoplanets, for example, here to LHS 3844b. This is just exemplary 2 albedo sets derived from lunar measurements, just to kind of see the difference here. And as you can see, we have this effect. If you just look at the red curves, there's the smooth model quite low, and then we have the higher emission for the rough model. Now, if we are only looking, for example, at secondary eclipse measurements, these effects will be very hard, or not likely to be detectable, because there's a lot of degeneracies, especially with the bolometric emissivity and the bolometric albedo. But however, if we look at the complete phase curve, we see that this has this quite unique effect where we have higher emission at low phase angles and then lower emission at higher phase angles. And this effect is different than the effects from the albedo and emissivity, which in this case, in this modeling approach, rather shift the amplitude of the whole phase curve up or down. Now, why is this important? In the solar system, we must include roughness to explain these measurements of the moon and of Mercury. If we don't do that, we can't correctly measure or model the measurements. And this also might mean if the conditions on airless exoplanets that have no atmosphere are kind of similar, then we would need to model it there as well, because not modeling it would lead to different biases. And if we want to retrieve other parameters, this could lead to wrong parameter retrievals. And this has been applied already in part, or is part of ongoing investigations as well. For example, by Brandon Park Coy, who will be the next speaker. He looked at the tentative brightness temperature trend and he looked into it if this could be one of the possible effects, but determined, okay, it's kind of hard to tell there. And also it's part of Sebastian Seba's James Webb observation GO 4008, where we try to directly probe the surface structure of LHS 3844b and actually determine if that's a smooth or rough surface. But again, huge challenges remain with other effects and different degeneracies there. That's my thank you. 2 quick shout outs. If you want to get more detail on the modeling and especially on those other effects, not just the roughness, but the albedo and emissivity as well, which are very important for this, have a look at Kai's poster. And tomorrow there will be a breakout session where we talk some more, hopefully, how the solar system investigations can help us with exoplanets. And I'm looking forward to great discussions there. Thank you.
Yes, okay, thank you. Are there any questions? And I would like to note here that please wait for the microphone so that also the online participants can actually hear the questions. And also keep your hand up so we can efficiently distribute the questions to other people. I see a question over there. So, there.
Hey, Claire Guimond, ETH, sir. I have just a quick question about when you say roughness, what kind of spatial scales are you talking about? Is this like regolith grain size, or is it more like crater size? And does it matter like relative to the radius of the body, or no?
It is on the smaller scales, on the Regulus scale. So on the very low scales where we still have some isolation, and this has the strongest effect, much stronger than on like a topography scale.
Thanks.
I'm going to follow up on that question. So I understand that you're using fractal structure as a proxy to the randomness, to our lack of knowledge of the distribution of the roughness. But don't you think that that will have influence and bias on the results? And how are you going to exclude the bias of the fractal nature of the fractal from the roughness? Am I clear?
Like how good of a proxy a fractal surface is for like a regular.
Exactly, right.
So far, Kai has extensively validated this model with measurements for the moon, and right now we're doing similar stuff with measurements for Mercury, and it has shown so far that it's a really good fit for that in terms of modeling.
Any Other questions? Yes.
Ollie Shortall, University of Cambridge. I was wondering, regolith is telling us something about the surface age of the planets. So in an exoplanetary context, I wondered whether there are going to be planets where you might have thought they're geologically active because they're tidally heated or resurfaced. So you could sort of a priori rule out kind of regolith-based kind of fractal models and think about different types of surface geometries for a resurfaced planet as opposed to an ancient surface like the moon.
Yeah, well, very good point. This is definitely one of the things. Maybe we could argue then if we don't see these effects, how does that come? Because we very much would expect that for similar planets or histories in the solar system. So that might mean something like extensive resurfacing is happening, or it's molten to a too high degree that we don't get this regolith layer or strong enough thermal gradients. But yeah, those are all then things to look into. If we actually don't see these effects at all, it must have a reason. Yeah.
Okay, thank you.
Right. Thank you.
Okay. And our next speaker is Brendan Coy, who's going to talk about the lava lamps survey. Looking at vaporized atmospheres.
Okay, can everyone hear me okay? So hello everyone, I'm Brendan Parkoy. I'm a third-year PhD candidate at the University of Chicago, and today I'm excited to present a first look at a JWST survey of 10 ultra-hot rocky planets in thermal emission. So we've heard a lot about how JWST is really opening up a new era in the characterization of these small rocky exoplanets. And one of the really big driving questions that we're trying to answer now with large surveys like the Rocky World CDT is what conditions are required for atmospheres on Earth-sized planets. So one way that we can look for these atmospheres is by observing a planet's thermal emission. So the basic idea here is that a thick atmosphere should be efficient at redistributing heat from the day side to the night side. And we see this pretty clearly in Venus. It's almost tidally locked, but there's no temperature gradient between the day side and the night side. In addition, if a planet does have an atmosphere, clouds can further cool the day side by introducing high bond albedo. So overall, observing a hot day side can rule out the presence of a thick atmosphere. We can make these observations more efficient than full phase curves by focusing just on this secondary eclipse, where we're just seeing the day side emission from the atmosphere or surface. So that sounds good in theory, but how do we actually do this in practice? So we do this by measuring the fractional change in light as a planet goes behind its host star. We can use this eclipse depth to derive an emitting brightness temperature and compare this to the maximum expected of a zero albedo bare rock. And this helps us put the planet in context of, for example, the solar system planets with and without atmospheres. So here I'm showing an estimate of what this ratio might look like for the solar system planets if they were tidally locked. And we can see for the terrestrial planet, GJ46b, we were able to rule out even thin Mars-like atmospheres to pretty high confidence with our data. So we've been able to do this type of measurement for a variety of rocky planets around small M dwarfs. And as you can see here, most of these have pointed towards bare rock surfaces or extremely thin atmospheres. However, we've shown in previous work that even if these planets lack atmospheres, trends in their day-side brightness temperatures can inform models of geological surface processes. So this is a little bit of a zoom in on the previous plot with some models overlaid, but it highlights how the current data point towards a strong trend in this ratio, which could possibly be due to space weathering, more efficiently darkening these closer in hotter planets. So if we go back to this plot and we expand this to look at planets that are hot enough to melt the entirety of their day sides, we began to see evidence for a population of lava world atmospheres. And we can also show these results in context of the cosmic shoreline. So again, this is the concept that a planet's ability to retain an atmosphere is mainly controlled by its surface gravity or escape velocity and its total high energy radiation received over its lifetime. And we can see pretty clearly that our non-detections of atmospheres on M-dwarf rocky planets lines up pretty well with our theoretical expectations. These small host stars emit a much higher fraction of their radiation in the XUV that helps promote loss. But if we start looking at these lava world atmospheres, we can see that these clearly defy our first order expectation that these ultra irradiated planets should quickly lose any sort of thick atmosphere to space. So this is what inspired the lava lamp survey PI'd by Megan Weiner-Mansfield. So this survey aims to use secondary eclipse measurements of 10 ultra hot rocky planets within this temperature range in order to better characterize this potential transition from a bare rock surface to a global thick atmosphere. And the data reduction is still ongoing, but we can see that our data reveal two pretty interesting points. One, these lava world atmospheres seem to become common past a critical temperature of about 2,500 Kelvin. And two, if we consider all rocky planets observed in thermal emission, they seem to follow a very prominent trend, with both the hottest planets and the coldest planets being less consistent with sort of this bare rock black body picture. But the exact functional form of this trend is still very uncertain. We don't really have theory in order to explain the data that we're seeing. For example, it could be a smooth trend like we see here, or maybe something like a step function, where there are just bare rocks and planets with atmospheres. Regardless, these results are pretty exciting because contrary to what we might initially think, these planets with atmospheres seem to span a wide range of planet densities. So here I'm plotting the uncompressed densities of these planets compared to an Earth-like composition as a function of their substellar temperature. And typically, we like to think that these underdense planets must have some sort of either volatile rich or extended atmospheric layer in order to explain their puffed up radii. But we can see from our measurements that planets with atmospheres might correspond more to this substellar temperature than actually their planet densities. And we typically think of these atmospheres as these very thin silicate vapor atmospheres in equilibrium with a magma ocean. So here I'm showing sort of a theoretical expectation of the latent heat redistribution from one of these thin silicate vapor atmospheres. And we can see that even if we up this pressure by 10 times the expected equilibrium pressure, this is not enough to explain the sharp transition that we see in our data. So like Joanna talked about a little bit earlier, this suggests that there must be additional processes affecting these planets' brightness temperatures. So one of these possibilities is that these planets host extremely reflective silicate cloud decks. So we've seen this in a hot Neptune at a similar temperature to the planets that we're looking at here, LTT 9779b. And there's some tentative evidence from Kepler that lava worlds generally have high geometric albedos in the visible. Another thing is that these could just be retained atmospheres from a volatile rich formation. These planets could have lost most of their atmospheres due to escape, but held on to just enough to still affect their heat redistribution and their brightness temperatures on their day sides. This might imply that these USP planets migrated recently. And lastly, we could simply just not understand how thick these silicate vapor atmospheres should be. There could be additional sources of internal heating, like tidal heating, that could lead to more production of silicate vapor, leading to sort of these globally thick silicate vapor atmospheres. So there's certainly a ton more points that I'm not able to get to here that might explain what we're seeing in our data, and I'd be happy to chat after the talk if you have ideas as well. But one way we can begin to try to break this degeneracy is through high precision emission spectroscopy. So the lava lamp survey was designed to go wide. We're looking at 10 separate planets, but not deep. These are all single eclipses. So currently our eclipse spectra lack the precision to make any sort of confident molecular detections, but future observations might be able to achieve the signals noise necessary to detect things like CO2 or CO or SiO2. So here I'm just showing some simulated near-spec data of 4 eclipses of one of these lava worlds, TOI 431b, with the previous Spitzer point, showing that with a moderate amount of time investment, potentially we'll be able to detect some of these molecular features. But we've seen from some of these previous observations that this will definitely be hard and harder than I'm showing here, but I'm still hopeful. So to summarize, our survey of 10 ultra-hot lava world planets reveal that thick lava world atmospheres become common past a critical temperature of about 2,500 Kelvin. And if we consider all rocky planets observed in emission, they seem to follow a strong trend in their dayside temperatures as a function of their irradiation. And going forward, high precision emission spectroscopy can reveal whether these lava world atmospheres are silicate or volatile dominated. And I'd be happy to take any questions.
Wonderful. Thank you very much. Are there any questions? Yes, I see over there. Question.
Charles-Edouard Boucaré, York University in Canada. Thank you very much for this great talk. You invoked mostly the atmosphere as the mechanism to redistribute this heat. What about maybe invoking the magma ocean or the interior of the planet? So maybe this sharp transition here, do you think this could be explained by a transition from maybe a shallow magma ocean to a large magma ocean, and what we actually see is the heat that is transported within the planet?
Yeah, so there have been some previous calculations of the expected heat redistribution efficiency of a magma ocean itself instead of the atmosphere. And these previous calculations have found that the magma ocean heat transport is orders of magnitude less than what's needed to explain, for example, our data here, and orders of magnitude less than if you did have some sort of thick atmosphere. I would refer you to KITE 2016. I know that's probably not a good thing to do, but they do a lot of calculations in that paper talking about this problem exactly.
Calculations are excellent, but they assume that the magma ocean is shallow.
Yeah.
So in that case, the heat transport efficiency is really low, as you mentioned.
Yeah.
But if the magma ocean depth is larger, then we can transport a lot of heat.
Yeah, I think that's a big unknown too. You have to make some sort of assumption about whether there's a lot of internal heating. Like, for example, a lot of these planets are in very tightly compact multi-planet systems. So tidal heating might actually be a big factor in determining, for example, how deep your magma ocean should be. So yeah, that's probably another big uncertainty in the modeling. But yeah.
Is there another quick question? Oh, over there, yes.
Thank you for a nice talk. I'm Rachel Zhang from Peking University. I have a question on this plot.
Yeah.
As the substellar temperature goes down, why there is a trend also going down?
Like here?
No, when on the other side, you
Oh,
even
here?
bring it to flat, it is also going curious.
Yeah, so I did have a paper on this side of the trend as well, and we think this is probably due to some sort of surface processes like altering the albedo of these planets. In particular, there's something called space weathering that, for example, the underlying rock of the moon is actually pretty bright, but when we look at the bond albedo, it's only about 0.1, and that's because it's been bombarded by micrometeorites and stellar radiation for billions of years. And we think that effect might be more efficient on planets that are orbiting closer in, so they're receiving more radiation. So that might be a possible explanation, but I think this might be a surface albedo effect.
Okay, thanks so much.
Yeah.
Thanks. Thanks to the speaker again.
Yeah, and feel free to ask me any questions after I talk too. Thank you.
So we're going to continue with Dan Bauer on the diversity of rocky planet atmospheres. And I've heard of the CONS system, but the CONS CL system, that's okay, maybe new to me. So please.
Okay, thank you.
Oh, the slide time.
Okay, excellent. Thank you for the introduction. So today I'm going to be talking about the diversity of rocky planet atmospheres, and this is work that I've been doing alongside the collaborators here that are now at various institutions, some of whom are here at this conference. So as means of summary, I'm going to be talking about a code that I've been working on called AppModeler. So this is an open source JAX-based code to compute volatile partitioning between planetary reservoirs. And in particular, it is for computing the partitioning between the atmosphere and the silicate mantle. I'll talk more about this. The code is all available on GitHub, so anyone is welcome to download and use it. We already have a range of science results available on arXiv. So the first 3 papers are accepted or published, and the final one, we are working on the revisions, but again, available on arXiv, so you can look into that. And also the code is available to the community to use and develop, and anyone is welcome to talk to me about that. So as means of introduction, when I'm talking about the partitioning of volatiles between the atmosphere and the mantle, I'm thinking in particular about this interface here. So we have a sort of canonical layered planet here, as we have for Earth and Venus. And this is looking at the planet early in its history when it had a magma ocean. We've already heard about magma oceans. Of course, from the exoplanet side, when we're thinking about observations and related effects in the atmosphere, we're thinking about this region here, usually the upper atmosphere. But actually, there's this important interface that occurs between the atmosphere and the magma ocean. And this is very important because it regulates exchange between the interior and the atmosphere. So basically what we can't see and hopefully what we can see. So this is exactly the region that AppModeler is capable of modeling. So an important aspect about volatiles is that they dissolve into liquids. Okay, so this is not just dissolving into, say, liquid water like we have for the ocean and CO2 at present day, but it's also volatiles that can dissolve into silicates, into melt. And so this is commonly referred to as a solubility or a solubility law. And if you just think of a simple solubility law, it's often expressed like a power law, such as this. So we have the amount of a volatile that is dissolved into a magma ocean, and this is proportional to some solubility constant. It relates to the partial pressure of that species in the atmosphere. And there's also a stoichiometric coefficient, which ultimately is tied to the underlying reaction that is controlling the equilibrium. The point is that alpha and beta depend on the species. So it depends whether you are considering CO2, H2O, CO, etc. And therefore, in order to deal with these interdependent solubility laws, a solubility library is actually included as part of the code. So fundamentally, what our modeler is doing is solving a thermochemistry problem, okay? So it's basically constructing an equilibrium reaction network with these gas species. It's also looking at the mass balance, and it's solving the whole system simultaneously to obtain the atmospheric composition. One of the novel aspects is that we can also include non-ideality that I'll talk about in the context of subneptunes. And it can also include condensates. So for example, graphite can actually condense at high temperature. So just because you're at high temperature does not mean that condensate's not necessarily relevant. Okay, a little bit about JAX. For those that think they have not heard about it, you have, okay? The reason for this is that JAX was one of the developments necessary for the Chemistry Nobel Prize in 2024. It's actually the engine that drives AlphaFold 2. It's very exciting for a range of reasons. And I just want to emphasize some of these because people typically think about JAX and some of the new developments in computational science as only being relevant for the machine learning community. But actually, a lot of the developments are equally as exciting for us working in numerical modeling. So basically what JAX does is it provides a lot of free features out of the box that we've been wanting for a long time in scientific computation. We want our codes to run fast. We also want to be able to rapidly construct large systems, to run many planetary configurations. And importantly, one key development is this automatic differentiation, which if you're familiar with it, will basically allow you to compute derivatives at machine precision. And this is excellent news if you are interested in writing efficient Newton solvers, for example. So I think there are already a range of applications for JAX in different communities, the robotics, protein folding. Physicists are looking into it for wave equations, and there's molecular dynamic simulations. And I think in the future, moving forward in our community, there will be also lots of applications. So now, for the sake of time, I would just like to zoom into some of the science results from the 2025 paper. I'm going to talk a little bit about what I refer to as TRAPPIST-1e models. Remember that in the context of what I'm talking about, TRAPPIST-1e means sort of the planetary parameters. It means the mass, it means the radius, etc. Okay, there's nothing particular as to why it needs to be TRAPPIST-1e other than that. So what we do is we solve for the atmospheric composition during the magma ocean phase. Okay, so we're looking at how volatiles partition between the atmosphere and the mantle during the magma ocean phase. We can run many, many models, and we vary things like the hydrogen abundance, C/H, and FO2. What we then do is we take these hot atmospheres and we isochemically cool them to 280 Kelvin, which is the equilibrium temperature of TRAPPIST-1. And what we then do is we look at what is the atmospheric diversity of this type of planet. And importantly, do we see condensates, including sulfur, water, graphite, ammonium chloride, for example? So first of all, one of the results which we've previously highlighted is that as you have a large magma ocean and as the reservoir increases, you tend to dissolve a lot of H2O. Okay, and when you do that, what you do is you elevate the C/H in the atmosphere. So with the elevated C/H in the atmosphere and the thermodynamic nature of CO, carbon monoxide, that tends to mean you find many models that form carbon monoxide dominated atmospheres. Okay, particularly when you have a large melt reservoir. The part then that we go to for the second calculation is we take these high temperature atmospheres, we cool and condense them to 280 Kelvin. And what we do is we ask the question of all the models that are available, how many of the models condense liquid water? Okay, and how much liquid water do we have? So this is all a self-consistent thermodynamic calculation. We don't impose the existence of water. We ask if it can be calculated in conjunction with the gas phase. And what we find, importantly, is that liquid water and graphite are typically stable beneath CO2 and CH4 atmospheres. Okay, so this is the typical configuration. Very interesting because, of course, we have, as was identified earlier, CO2 atmospheres in the solar system today. There are other possibilities of atmospheres that can also support water and graphite, which are interesting but much less probable. What we then do is we identify atmospheric signatures that can correlate with surface condensates. So we're looking at the relationship in order to say, if we find certain species in the atmosphere, what does that tell us about the surface and the potential for condensates to exist there? So we find, for example, sulfur, graphite, and water, and we have correlations with various atmospheric species that are all described in the paper. So moving on to sub-Neptunes briefly. So we perform a similar task for a canonical sort of sub-Neptune. Again, we're solving for the atmospheric composition in equilibrium with a magma ocean. In this case, we are just constraining a few parameters or setting a few parameters just to limit the parameter space. But in principle, you are free to use as many parameters as you wish, of course, and explore the space. And we take K218b just as a canonical case, just to give us the size and radius of the planet. So we are effectively modeling K218b as a gas dwarf. So the key aspect when you're considering sub-Neptunes is that the interface pressure, so the pressure due to the atmosphere, is sufficiently large that gases now are non-ideal. Okay? So this would be the ideal case where the fugacity coefficient is unity, but you can see you have orders of magnitude departure from this. Okay? And this should obviously be accounted for if you are thinking about large atmospheres. The reason this is important is because the solubility ultimately also depends on the fugacity coefficient. So when you are a real gas, you also are greatly enhancing the solubility of species into the magma ocean. So these figures are all from the paper, but again, you can see here for the interior mass fraction of hydrogen and carbon for a real gas case that is larger than for the ideal gas case. Okay, finally, we look at the role of the C/H ratio, which I think is very interesting because people typically approach the question of sub-Neptunes from hydrogen dominated, and maybe that's correct. But if you start to add a little bit of carbon into the system, you actually find that you can transition from a regime that is H2 dominated to a regime that is actually CH4 dominated, okay? Remember, this is the chemistry at the interface, okay? It's not necessarily the chemistry that you observe, which is at much lower pressure and temperature. But nevertheless, this can give rise to some very interesting trends in terms of the C/H and C/O. Finally, there's always the question of what does carbon do? The reality is that at the minute, the experimental data is not able to decisively tell us whether or not carbon prefers metallic phases or silicate phases. So it remains an open question as to how much carbon goes in the core, a metallic core. But we do know from the solar system that we do see CO2 atmospheres. So clearly not all carbon goes into the core. Okay, I will leave my takeaways on screen and I'm happy to take questions.
Wonderful, thank you very much. Are there any questions over there? Yes.
Yes. Hi, Afonso Mota from the University of Porto. I'm really interested in your results and particularly for TRAPPIST-1e. I wanted to ask, maybe I misunderstood. You mentioned the temperature of 280 Kelvin. I think you talked about equilibrium temperature, but I thought it was much lower for TRAPPIST-1e. So I was wondering how you reached that value and if you guys tried different values of temperature and if that affected, of course, the liquid water, but other parts of your results as well, either lower or high temperatures. I don't know if you went.
Yeah, sure. Yeah, so 280 Kelvin is the equilibrium temperature, as far as I'm aware, or thereabouts. Of course, you can change, absolutely, you can change the temperature. Of course, 280 Kelvin is nice because you also get stability fields for all the condensates. Clearly, if you go too high temperature, you won't end up with any water. Graphite is generally quite stable, so you will tend to produce quite a lot of graphite at different conditions. But absolutely, you can, I mean, all the scripts are part of the model, so you can change the temperature and look at the speciation. Yeah.
Right. Thank you.
Other questions? Yeah, over there.
Is this on? Okay. Adriana Postuma from UC Davis. So you have there on your fourth item is enhanced solubility of CNH at a high temperature and pressure. Do you think that has anything to do with what was going on in the previous presentation about a big change in atmospheres at about 200 or 2500 Kelvin in very, very hot closed magma oceans? Like, is that high solubility potentially leading to the differences that we were seeing just in the previous presentation?
Yeah, to some extent, but remember that as I showed for the fugacity coefficients, this tends to be a relatively smooth transition. So it's not sort of like a phase transition where you would sort of see maybe a step change in atmosphere size. It would still be relatively smooth. And again, remember that these calculations are all strictly at the interface at high pressure, which is not necessarily what you observe. But certainly, yeah, for high pressure planets, this should be a consideration in the modeling.
Okay. Okay. Thanks, speaker again. Thank you. And then we continue with Yichen Gao on the convective inhibition leads to different climate regimes on Haitian planets. So it's nice that the conclusion is already in the title, so we don't have to listen to the talk. Oh. Don't do that.
Thank you.
Please. Thank you.
Thank you.
The floor is yours.
Can you hear me? Okay. So I'm Yichen Gao from Beijing University, and today I will talk about Haitian world and some very interesting features of their climates, if they were true. And I really want to thank my supervisor, Daniel Cole. Even he didn't come here, he sent 3 of his students to this amazing conference. And I hope you haven't been so tired of hearing the word Haitian, but so it's a hypothetical type of exoplanet that has ocean and hydrogen atmosphere, and they are really attractive because they might be the easiest to characterize the potential habitable exoplanets. And because their atmosphere is full of, have plenty of moisture, so convective inhibition can play an important role in its climate. Just like this figure show, with inhibition, the chemical abundances can change a lot, and also the temperature of its interior can change up to 1,000 Kelvin in the interior. So what caused the convective inhibition? So here I just plot the density against temperature for a air parcel with fixed relative humidity at a fixed pressure, and you can see if it's completely dry, the density just decreases monotonically with temperature. But if there is water, as you heat the air, you continuously adding water to it, so the density can actually becomes higher as the air is heated. Sorry. So at the point where this trend changes, there is a incubation temperature. So above this temperature, you cannot trigger convection by warming the atmosphere, because as you warm it, the density actually gets higher and it won't rise. So this phenomena because it inhibited the convection, the atmosphere will accumulate energy under this inhibition, and this will makes the interior very hot. And once the convection happens, it can be a very large one, just like what we believe to be happening on some of the gas giants in our solar system. But here, we are focusing on Haitian planets with very small atmosphere, so that the surface is still important. So when the surface temperature is below the T inhibition, we just assume the entire atmosphere is a troposphere, so the temperature decreases linearly with height. And if the surface temperature is above the T inhibition, we assume a very thin inhibition layer near the surface. So it's like a temperature jump at the surface. And we also decrease the amount of water in the upper atmosphere because the inhibition layer will prevent the water be effectively transported upward. So with this simple model, we add gray radiation to calculate the OLR. So if we assume the albedo is 0, this y-axis also represents the stellar flux that is in equilibrium with this atmosphere. So if the atmosphere starts cool, we can get this S inhibition, above which the convection is inhibited. And if we start hot and cools it down, we also get a S convection at which the convection is resumed. However, interestingly, these two values are not the same for thin atmosphere. So we get these two different situations. If the S inhibition is higher than the S convection, we have a region that we have a range of stellar flux that can be in equilibrium with both a convective state and the inhibited state. But if the converse is, however, if the S convection is higher than S inhibition, we have this range of stellar flux that cannot be balanced by neither inhibition state or the convective state. And we plot this S inhibition and S convection on the 2D parameter space with installation as x-axis and the total thickness of atmosphere at y-axis. We can see that when it's cool and has a thin atmosphere, it's always convective, while on this region, it's always inhibited. But on the boundary, we can see that at this regime, this bistable, so it can either be a convective state or in the inhibited state. And at this regime, it's oscillating, so neither state is stable. And we also confirm this prediction with our 1D model. And in the interest of time, I won't show all the results we have. Yes, and we found that yes, on the boundary, most of the boundary is the bistable regime, and we have two different dashed lines here. One on the left, we assume the upper atmosphere is completely dry, so there's more difference between a convective state and the inhibition state. So there is a large bistable regime when the inhibition is strong and the upper atmosphere is dry. Yes, and here I showed the time series of TOA net flux and also the surface temperature for 4 cases in each regime. Blue line is the cool start case simulation, and the red line is the hot start one. For the convective regime and the inhibited regime, both lines converges after some time. But in the bistable regime, although the net flux has been in the equilibrium, they have very different surface temperature. And in the oscillating regime, they are oscillating. And I would like to show a video of the oscillating regime. So here the red line is the specific humidity and black line is the temperature. You can see here it's in the convective regime and convecting, and it jumps back, so on and so on. So to make things more complicated, there's multiple equilibria in the inhibited regime. So in the previously, we assumed that the inhibition layer is only very thin near the surface, but in reality, we don't know how thick it is. So in our simulation, we use different initial condition and also perturbating it by adding more water. And you can find that the thickness of the inhibition layer can vary a lot, which also makes the surface temperature changes a lot. So the takeaway message is there are bistability and oscillation, and at where it starts to get inhibited, and also there can be multi-stability for very warm Haitian planets where we cannot really decide how thick is the inhibition layer, and it has implications for observation that because convective inhibition can really limit the vertical mixing, but the detail of it cannot be resolved in 1D, so we are very uncertain to say something about the chemical abundances of the hydrogen world. Thank you. I'll take questions.
Very much for this. Thank you very much for this very interesting talk. Other questions? Really?
Hi, thanks. Shamira Miguel from Leiden University and Estron. So in the diagram that you showed with the different regimes, there is like another axis that I'm missing because which is the humidity that you are using, because this regime depends strongly on the amount of water that you have in your atmosphere and also on your background gas. So I was wondering what you are considering here.
Yeah. Here I'm considering a mixture of, for the background gas, it's a mixture of hydrogen and helium, and with a mean molecular weight around 2.5. I forgot the exact number. And here the dashed line on the left side, we assume a completely dry upper atmosphere in the inhibited state. And for the dashed line on the right side, we assume still assume a somewhat moist upper atmosphere.
Over there.
Hey, Will Meisner from Carnegie Science. Really nice talk. I just wanted to make sure I was thinking about this in the right way. So in terms of your kind of bistable versus oscillating states, I was wondering what sorts of optical depths the inhibition layer is happening at, and if it's because it's like optically thinned down to that leads to the oscillation or something like that.
Yes, that's true. In the oscillating regime, the whole atmosphere is optically thin, and when it's optically thick, these two lines converge. Yes.
And is it because it's optically thin that you get
and
this
that's why we only consider a small atmosphere.
Okay, thanks.
Thanks. One more question over here.
Hello, Xuecheng Yang from ETH. My question is, your models look very much similar to double diffusive convection, with your temperature being their combined effect of temperature and salinity. And also the observed regimes also look very much similar to that. So my question is, have you been aware of this? And have you compared different models?
Sorry, I didn't hear. Similar to what?
Okay, so in oceanography, people study double diffusive convections. And so the effect of temperature and salinity are kind of contradictory. Yeah. So the combined effect can be something like a U shape. So I'm thinking about that the temperature you use in your model is basically the combined effect of their temperature and salinity.
Yes, it's very, it's similar to that. And I think in one paper in Lecon 2017, they have a discussion about double diffusivity in this scenario. Yes, and I think here we didn't include we didn't include double diffusivity in our model, so we only diffuse the moisture.
I mean, so you observe like 4 regimes in your model, right? Yeah. If you look at double diffusive convection, I guess they also have like 4 regimes.
Okay, thank you.
Which look very much similar to that. So.
Thank you.
Okay, I understand we have one online question, so maybe.
Yeah, so Edward Barrier online is asking 2 small questions. First, what's your vertical resolution like in the inhibition zone? And do you think that this affects your result? And then have you tried including other atmospheric absorbers such as CH4 or CO2? And what difference do you think this would make in terms of the installation thresholds?
Yes, and in our simulation, we use around 80 vertical levels for the, yes, they are evenly divided. And we also test the sensitivity to different grids and this diagram, sorry, I didn't show the, I can show the simulation results. Yeah, these are our simulation results, and I think they are not very sensitive to the different grids. Yeah. And yes, we didn't include other species in our model today.
Okay. Thank you. Thank you very much. And then for the final talk of today, we have Jordan telling us about planetary albedos, and that they are limited to the above cloud atmosphere.
Okay, hi everyone. I'm Sean. I'm a postdoctoral fellow from ETH Zurich, and I'll be talking today about some research that we published a few months ago with collaborators Ollie and Sasha about how the planetary albedo of an exoplanet is limited by the above cloud atmospheric absorption of the stellar radiation, and in quite a convenient way such that we can actually retrieve a limit on the albedo based on a transit spectrum. And we're going to apply this today to everyone's favorite sub-Neptune, K218b, to ask whether it really can be potentially habitable, a Haitian world, right, based on the observations that we already have. Okay, so this is our familiar Kepler statistics plot of the size distribution of exoplanets. And we have Earth here, Neptune here, and this is our sub-Neptune peak. Right, and this is a Rocky Worlds conference, so why am I talking about sub-Neptunes? Well, because we don't know what they could be made of, right? They could be a water world with a supercritical water hydrogen envelope. They could be a water world where the water is even condensed out into high pressure ice phases and a surface liquid ocean underlain by a very thin hydrogen atmosphere, sort of so-called Haitian idea. Or they could be true bona fide rocky planets, right? And all of these fit the sizes of sub-Neptunes. They even fit the bulk density when we have mass measurements as well as the radii. So it's a degenerate problem. So what we can do is we can take a transmission spectrum from high in the atmosphere, and this is the famous transmission spectrum for K218b from Madhu's 2023 paper. But it turns out that even the transmission spectrum is degenerate, right? The chemistry here can still be fit by both a water ocean or a magma ocean model. So is there anything else that we can do to try and break this degeneracy? And so I'm going to focus on this idea of a water ocean or a Haitian idea, because this requires climate stability, right, for a surface liquid water ocean. And if we think about this, we have this very well fleshed out idea of an Earth-like habitable zone. We've been thinking about this for decades. We have 1D models, 3D models, weathering feedbacks, thermostats, atmospheric dynamics with albedo feedbacks, right? And it's a very well fleshed out concept. For the Haitian habitable zone, this was actually only very recently addressed. First by Innis 2023, who find the Haitian runaway greenhouse under a 1 bar atmosphere or a 10 bar atmosphere to be much further away. And this is because of the effects of convective inhibition, which we've just had a really nice introduction about, where we have water in a hydrogen background and water is heavier, and so we get a mean molecular weight gradient, and so it pushes this out much further. Oh gosh. What's that? Okay, so K218b sits here. Now, just because it receives a similar Earth installation flux doesn't mean that its climate physics pertains in any way to an Earth-like model of habitability. So it's actually very far away from its kind of first estimated runaway greenhouse limit. And the argument being posed is actually that, well, this is a kind of new one-dimensional cloud-free model. And so actually, if we can just increase the cloud albedo, then we can bring the habitable zone to K218b. Which is a really interesting idea, right? It kind of reveals something going forward, that if we're going to be observing exoplanets that are not necessarily Earth-like, not even Earth twins, then actually we're going to see arguments of this nature more and more, I think. And so I think it's an important point now to ask this question, really, are all albedos possible, given observational constraints, in this case, a transmission spectrum? And I've got an analogy for this. So imagine you're looking in the mirror, it's very reflective. If you throw a blanket on top of this mirror, it's not very reflective anymore. If you throw something else on top of it, right, say glitter, whilst the mirror isn't doing any any reflecting, the thing we've obscured the mirror with is intrinsically itself very reflective, and so we still get some reflection. And this is kind of a bit like transmission spectroscopy, right? Turn this on its side and imagine that our cloud top is this mirror, right? We might not be measuring any properties of the mirror, but what we are measuring, and quite explicitly, is the thickness of the blanket on top of it, the above cloud atmosphere. And just normal gases, greenhouse gases like methane, yes, they absorb lots of planetary emission, but they also absorb some of the stellar emission, the starlight. They have to, because that's what the transit spectrum is, right? That's what we're measuring, the optical depth to the starlight as a function of wavelength. So if we see absorption features, then we're necessarily limiting the maximum albedo you could ever attain from a perfect mirror. Alternatively, if we see scattering features, then it's a bit more complicated. So we derived an analytic approximation for this effect using the two-stream equations from everyone's favorite climate Bible. We can solve for perfect reflection at the bottom boundary to represent just a perfect gray mirror. And lots of algebra later, we get a nice, neat analytic approximation for the planetary albedo, or the upper limit on the planetary albedo. It's actually not quite so neat. This C term hides a whole load of crap, but it's a function of optical depth and single scattering albedo. Where this scattering albedo is basically just telling us what proportion of that opacity above the clouds is due to scattering versus absorption. So what does all this really mean? Well, we can plot this up as a function of tau infinite, right? The opacity above the cloud deck, and with contours of W0. We can see that if we had our perfectly reflective cloud at very low optical depth, so not very much above cloud opacity, then it's just like our mirror. The deeper down we go, the more blanket we're throwing on top of this mirror. And so even though we've imposed perfect reflection as a boundary condition, we still end up with a very low planetary albedo. Whereas if we have a very scattering above cloud atmosphere, then it doesn't care what's happening with the mirror because the atmosphere itself is already very reflective. So these are our regimes. To make this a bit more physically useful, we have to use a numerical model. We do a multiple scattering line-by-line model where we can calculate the fluxes across layer interfaces in pressure space from the top of the atmosphere down to some assumed cloud top pressure level. You can calculate the reflectivity and the transmissivity to direct and diffuse radiation, where diffuse radiation is the already scattered component. So it accounts for multiple scattering. The details are all in this sort of Brieglev 1992 paper, and it's been used a few times since. Basically, we get this, all right? So instead of an optical depth axis, we have a cloud top pressure axis, so it's a bit more physical. And I'm showing now what this looks like as a function of the methane in the atmosphere. So we can see for a perfectly reflective cloud, again, the deeper we are, so the thicker the above cloud atmosphere, and or the more methane there is in that atmosphere, the stronger this constraint is. And in this limit, it can actually become a very strong constraint. So let's do this for the retrieved parameters of K218b. If we take the Madhusudan et al. 2023 median values for methane, for CO2, then we can take the median retrieved cloud top, and this imposes an upper limit on the albedo. And we can compare that to these habitability criteria for different surface pressures from Innis 2023, LeConte 2024, and we can see that it's quite far from the threshold. Now, we might not be interested in a perfect reflector. We might want to investigate different cloud albedos, more realistic ones, and we can even invert this problem to ask the question, well, if we want to enforce a habitable climate, what would the transmission spectrum look like based on the cloud top pressure that's required as a function of the cloud albedo. And you can see now how there's this one-to-one connection between the transmission spectrum and the albedo. Of course, these retrieval parameters have their 1 sigma error uncertainties on them. And so we can alternatively actually think of this as a retrievable parameter and marginalize over all of those posteriors. In which case we get something like this, a posterior distribution on the likely albedo. And this is marginalizing again over the full cloud albedo going into the model, right, from 0 to 1. We might alternatively want to still try and retrieve an upper limit on what we might expect, in which case we can isolate high cloud albedos and we can see what proportion of this posterior they're contributing to. Now, there's another added subtlety to this, which is the wavelength coverage. See, another part of the argument is that actually we could have very enhanced scattering slopes due to some haze parameterization that we just simply don't see very much evidence of in the spectrum itself because it's at shorter wavelengths. And so if we take these suggested haze parameterizations from this paper, then we can also calculate what the albedo would be in that case, right? It's replacing our blanket with our glitter. They still fall short from the kind of canonical habitability estimates for what albedo would be required, but some interesting work coming lately from Edouard Barrier in Cambridge is doing GCM modeling, where if we enforce such a high haze scattering in the upper atmosphere, it actually creates an anti-greenhouse effect that cools the surface, and so you end up with different albedo requirements. So here we have 1 bar, 5 bar, and 10 bar. So the idea really is that if you have a sufficiently thin above cloud atmosphere, sorry, a sufficiently thin surface pressure, thin atmosphere, and a sufficiently high haze scattering, then you can tune a habitable K2-18b if you really want to. But this still isn't the end of the story. More recently, Hugh et al. 2025 presented some more data, some more transits, and we have 10% methane with more constrained posteriors and no evidence of clouds or hazes. So as with any other retrieved parameter, we can rerun this exercise and we get a much more tightly constrained albedo. And again, if we want to know what this kind of upper limit is, we're predicting an upper limit on the albedo of K2-18b of about 0.2 to 0.25. So these are my take-home messages. Cloud albedo is limited by the optical depth to starlight above the clouds. It kind of sounds a bit trivial, actually, when we think about it, but it's never really been formalized officially. This albedo constraint is potentially limited by the wavelength coverage, but the implication there is just that K2-18b to be a Hessian requires very finely tuned haze properties. Thank you.
Wonderful. Thank you very much. Any questions? Yep. Here.
Hey, Tad from Oxford. So when you go from the retrieved cloud top pressure to what matters for 1D rate of transfer calculation, you need to make some assumption about the geometry, because in transmission, you're measuring the slant optical path, but then you need to convert that to a vertical optical path. And so does that greatly change your cloud top pressure? And does that affect any of your results?
The idea really is that we're just taking the retrieved posteriors and then we're modeling it as if it's a column of atmosphere, but we're doing the angular distribution with Gaussian quadrature. So it should be accounted for. Unless, of course, the object itself isn't uniform spatially, which is a whole kind of worms, I suppose.
Any other question? All the way there in the back, I see.
Bennett Skinner, McMaster University. This is all for K2-18b as one specific case. Have you looked at any other planets and have you found anything interesting?
It's a really good question. I haven't yet, but we're in the process of further generalizing and speeding up the model so we can do a population level study of all the subneptunes observed so far with transmission spectroscopy.
Very quick question.
You can.
So follow up on the other one. How do you choose those planets?
How do we choose one, sir?
Yeah, so follow up on the previous question. So you said that you haven't looked into other planets, but you are going to. So how are you going to choose the planets?
Everything that we have data for. Yeah, there's not so many. Sub-Neptunes, right? So Neptunes with transmission spectroscopy with Webb. What's this, about 10 now, is it? We do all of them. Yeah.
We do all. I think that's a final good. Oh, there is one online question. Okay, yeah, we can do that.
Hi, it's Edward Barrier saying, me again, thanks Sean, really nice work and a principle that would be really important going forward. I liked comparing to the best fit haze parameters. Have you tried varying the hazes and seeing what albedos emerge? For example, 1,000 times Rayleigh scattering.
Yeah. Is this? Yeah, that's backwards. So that is what we've got here. It's not even 1,000 times Rayleigh scattering. The parameterizations that came out of this paper were a bit extreme. They were maybe 10 to the 6, 10 to the 7 times scaling factor, which is why the albedo shifts up so much and becomes very tightly constrained. So yeah, I think that answers the question.
Thanks.
Wonderful. Thank you very much. And let's thank all the speakers of this amazing session. It was very nice. And then now we have a reception, which is over here, which starts, I think, now, because all the speakers were so amazingly on time. And tomorrow morning, we start at 9. So again, back here at 9 tomorrow for more great science on rocky planets. Thanks.